Hello, everyone, and welcome to all the speakers and delegates for the third day workshop on Liutex and third generation of Vortex identification for engineering applications, which is an integral part of Aerospace and Aeronautics World Forum. And now we'll begin with our talks.
Good morning, good afternoon, good evening, everyone. My name is Yishen Gao from Nanjing University of Aeronautics and Astronautics, China. Today, my topic is Liutex-based integrated field inversion and machine learning framework for turbulence modeling. First, I would like to say it's a preliminary idea, so the results will be presented in the final paper. My topic contains three parts. First, motivation. Second, RS decomposition. Third, integrated field inversion and machine learning framework based on Liutex. First, we talk about the motivation. As we all know, the current turbulence model is not accurate for separated flows. For example, SA model is used to calculate the SAO9 airfoil flow we can find at low angles of attack. The results of SA model agree with the experiment, but at a larger angles of attack, large discrepancy appears as shown in the left figure. We can see the figure here. At large angles of attack, large discrepancy appears. This problem can be also found in other turbulence models like K epsilon model, SSTK omega model, as shown in the right figure here. It's because the separated flows violate some assumptions used in the turbulence model, such as the equilibrium assumption of the eddy viscosity model. In the SAO9 airfoil flow, we can find large separation region leading up surface at large angles of attack, as shown in the figure here. The presence of adverse pressure gradients results in separate flows and violates some assumptions. So the turbulent model will overpredict the eddy viscosity. Separation region will be too far after and too small, and we will overpredict the lift coefficient. You can see here, lift coefficient is overpredicted. Usually, we can find some closure constants used in the turbulence model. Here we list some closure constants used in the SA mode. These constants are not suitable for separated flows because closure constants are usually calculated based on attached flow over simple geometries. On the other hand, even if we use the exact values of turbulent kinetic energy and dissipation rates, the performance of a turbulence model cannot be improved. Sometimes use of exact values will deteriorate the performance of turbulence model. In recent years, machine learning is a core technology for scientific computing. It can be used to accelerate the speed of direct numerical simulations. It can be used to improve turbulence modeling, and it can be used to develop reduced order models. These ROMs can show important coherent structures and provide valuable information about the flows. So it's used for representation and flow control. We believe Turing's model will continue to be indispensable for engineering application in the near future, so we would like to use machine learning and data to improve turbulence model. But if we use data directly to make a prediction, we need huge data. And if we directly inject high fidelity data to the model, the high fidelity data and turbulence model are inconsistent. So the best approach is to formulate and solve an inverse problem to generate the information consistent with the model. We can use experimental data to improve RANS models. We can use LES DNS information to improve RANS models. Our objective is to correct the turbulence model. First, we formulate an inverse problem to incorporate higher fidelity data, such as sparse experimental data. Second, we generate a machine learned model based on Liutex data. Third, we correct the turbulence model with the machine learned model. Because the complete Liutex data can be obtained by RS decomposition next, we will briefly introduce RS decomposition. RS decomposition is used for velocity gradient tensor decomposition. In the left figure, the black XYZ represents the original coordinate system, and the blue XYZ represents the principal coordinate system. The z-axis of the principal coordinate is along the direction of the real eigenvector. The xy axes are determined by the coordinate rotation so that the first two diagonal terms of velocity gradient tensor are equal. In the principal coordinates, the velocity gradient tensor can be decomposed into a rotation part and a non-rotation part. The rotation part is also called Liutex tensor. Liutex tensor is an antisymmetric tensor. The non-rotation part contains shear, compression, or stretching effects. Here, lambda CR is the real part of the compressed eigenvalue, lambda R is the real eigenvalue, and other variables are the shear. The shear variables can be used for vorticity vector decomposition according to our previous work. The main part of vorticity in coherent structure is shear, as shown in the figures here. One actual proposed an explicit formula to calculate Liutex directly in the original coordinate system. The explicit formula for Liutex is given on the right here. So we can calculate Liutex using eigenvalue, real eigenvector, and vorticity. Using the explicit formula for Liutex, we can perform the RS decomposition in the original coordinated system, and coordinated rotation is avoided. NR can be further decomposed into the stretching compression part and shear part in the original coordinated system. Here SC is the stretching compression part and S is called the shear part. Using RS decomposition, we can prepare complete Liutex data for field inversion and machine learning framework. In the following, we discuss integrated field inversion and machine learning framework. In this work, we would like to use field inversion and machine learning framework to crack the SA model. The standard SA model is given here. In SA model, a working variable, new theta, is introduced. The equation presents here. The equation presents the transportation of new theta. On the right-hand side, the source term includes the production term and the destruction term. Intermediate variables and closure constants for SA model is given here. As mentioned above, the closure constants are usually calculated based on attached flows over simple geometries. Once the solution is obtained, we can use new tilde to calculate turbulent eddy viscosity from the first equation, and then the turbulent eddy viscosity will be used for Favre average Navier-Stokes equations. Although SA model contains closure constants, the calibration of these closure constants are insufficient for separated flows. The main source of discrepancy is the functional form of the model. Therefore, a spatially varying correction term beta x is introduced to production term. So the original production term will be multiplied by the correction term beta x, and the corrected equation is presented as follows. Feeder inversion and machine learning (FIML classic) is proposed by Raisami and co-workers. In the first step, inverse modeling is created to infer the spatial distribution of model discrepancies, and then machine learning is used to reconstruct discrepancy information from an inverse problem into correct model forms. The schematic of FIML classic is shown in the figure here. The first step is field inversion. Here we use lift coefficient as an example. CLEXP means lift coefficient from experiments. CL beta is lift coefficient from the corrected model. We can see here there is a large discrepancy. So an object function J beta is introduced to measure discrepancy. The last term is called regularization term. And lambda is a user-defined parameter to control the regularization. We solve an inverse problem or optimization problem which minimizes J beta to find the spatial distribution of beta x. The inverse problem can be solved by a gradient-based method. The required gradient is obtained by a discrete method. Discrete adjoint method, because discrete adjoint method is very efficient for gradient computation. The total derivative dj d beta is equal to partial j partial beta plus beta bar transpose multiplied by partial r partial beta. Here, R means range equations including turbulence model equation. Beta bar is a vector of adjoint variables. It can be solved by adjoint equations, a system of linear equations. Once the spatial distribution of beta x is obtained, a function beta eta is generated by neural network to approximate beta x. Here, eta means local features. The right figure shows the structure of a neural network. The input consists of local features. In the hidden layer, each input to a neuron has a weight, Wij. The weight multiplies its input, and then all weighted inputs are summed to create the input to the neuron. The neuron applies an activation function to create the output of the neuron. Here, tanh is used as activation function. The output of the whole neural network is beta. Beta propagation algorithm is used to train the neural network. FIML classic can improve the prediction of SM model for separate flows, but inconsistencies exist between the data and the modeling environment due to discrepancy between inverse model and ML model. Even if the inverse problems are solved perfectly, the discrepancy cannot be removed due to ML training error. So integrated inversion and learning is required to improve FIML classic. Holland et al. Proposed an integrated FIML method called FIML Direct. It replaced the original object function by the following form. In this case, the neural network weight becomes design variables. The left figure shows the difference between FIML classic and FIML Direct. In FIML Direct, the inversion and learning are integrated, while in FIML Classic, the inversion and learning are separated. So the discrepancy between inverse model and ML model has been removed in FIML Direct. In FIML Direct, the gradient becomes djd dw. Using the trend root, djd dw is equal to djd d beta multiplied by d beta dw. djd d beta is obtained by discrete adjoint method as used in FIML Classic. D beta dw is obtained by backpropagation algorithm. In this work, we modify the open source CFD software SU to equip with FIML direct method. We add the calculation of RS decomposition and choose Liutex-based variables as features, such as Liutex magnitude, Liutex vector, and components, Liutex and tree vector and components, Liutex tensor, non-notation tensor. The best feature set is under research, and several separated flows are used to test Liutex-based framework. The result will be presented in the final paper. That's all for my presentation. Thank you for listening.
So for your presentation, anyone got questions? Okay, I have a question, Dr. Gao. Please tell me can you tell the difference between SU2 and OpenFOAM? Because these two softwares, the difference between this.
Okay, okay. I'm not very familiar with OpenFOAM, but in my opinion, okay, OpenFOAM is used for incompressive flows because it mainly use the simple method to solve the incompressible flows. SU2 is used for compressible flows because it uses density-based method. I think it's the main difference.
Okay. And you said you use machine learning, right? You use X, R, Y, R, Z to be the input.
Right.
And what is beta? I didn't get your explanation about the
yeah.
beta.
I explain it again. And beta is the correction for the production term in the SA model. You see here, beta.
Mm-hmm.
Yeah. So what we do is to get the function. The input is Rx, Ry, Rz, for example, and the output is beta. We use machine learning to find the function of Rx, Ry, Rz, and beta.
Okay. Okay. So anyone has questions? Because we still have 5 minutes. Okay. So let's have a break. 5 minutes break. And the next presenter is Zhang Shuang. Okay.
Hello, everyone. I'm
sorry. We still have 2 or 3 minutes break because we need to start at 8:20. Okay.
Okay.
Thank you. Okay, the next presentation will be given by Shuang Zhang from the Shanghai Institute of Technology, China, and his topic is an extended similarity in channel turbulence. Let's welcome Dr. Zhang. Can you share your screen?
Hello.
Hello. Can you share your screen? Okay, welcome.
Hello, everyone. I'm Shuang Zhang, a postgraduate student from the School of Science of Shanghai Institute of Technology. The topic of this report is an extended similarity in channel turbulence. And I will elaborate on my report in the following 4 aspects. First, the Liutex similarity hypothesis. Second, physical model. Third, results and discussions. Finally, conclusion will be established. Next, we give a Liutex similarity hypothesis into dimension channel turbulence. The Liutex spectrum in the integer range is equation 1 by dimensional analysis. The mean displacement rate of square of Liutex magnitude. Equation 2 is conceptually proposed to describe Liutex similarity, which is similar with displacement rate of astrophy into dimension and turbulence. Liutex vector string strength strings equation 3. Liutex vortex number density is NA directly proportional to the negative 2 power law of area A based on our simulations and base cell figure 1 the number of vortex density NA as a function of vortex area by the way of Liutex. Next, in order to verify this theory, we select IBLBM and figure 2 show that the sense of the wall computational demand is 60 diameter. Multiply 10 diameter of the 5 cylinders in the vertical rise is 50 with a spacing of 100. The diameter of the cylinders in the 2 horizontal rise placed at 50 from the channel wall is 20 with a spacing of 100. Figure 3 and Figure 4 show that there are large number of vortex structures with different scales. Moreover, it is obvious that ridges in the near wall and at the edge of the vortex structure are absent, while the sharing may have occurred. This is mainly due to the fact that the Liutex can extract the radial rotation part from the filter motion. According to Dr. Xu put forward to the Liutex spectrum, Figure 5 shows that the Liutex spectrum of 2 dimension turbulence matches the negative 5/3 law in small scales of the rate is much larger than velocity spectrum. And the Figure 6 shows that the Liutex spectrum for different Linus number match with the negative 5/3 law, while in small scale, which prove the Liutex astrophic hypothesis is independent of Linus number. As Pauling, we carry out new similarity law about the Liutex structure functions. First, the velocity structure functions, SP, CP is the estimated scaling exponents, and Liutex structure function, Liutex P, cosine P is the estimating scaling exponents. Figure 7 shows the results of the velocity structure functions SP with different orders, including the highest order P equal to 12. And Figure 8 shows the result of the Liutex structure functions. It means that Liutex structure functions may be independent of scalars, regardless of moment orders. Figure 9 shows that the scaling exponents of Liutex structure function xi p equal to 0. Liutex structure functions are independent of scalars. Equation 5. We lost option numerical result fully compatible with our theory, for which the exponent are predicted to be extracted there. This is the conclusion. First, Liutex similarity hypothesis in channel turbulence is proposed, which donates that Liutex similarity is uniquely and universally mandated by the scalar. Liutex vortex number density and mean displacement rate of square of Liutex magnitude. Second, Liutex spectrum matches the negative 5/3 law, while in small scalars, of which the rate is much larger than that of velocity spectrum. Each team in Liutex spectrum has a clear physical meaning. Our Liutex similarity hypotheses are also extended to three dimension turbulence, which can explain the physical meaning of phi in three dimension Liutex spectrum. Finally, a new similarity law about the Liutex with structure function is carried out. This result shows that our grooves of the Liutex structure functions are almost parallel in large scalars, which are different from velocity structure functions. Liutex structures functions are independent of scalar. Liutex be direct proportional to the zero power law of L. That's all. Thank you.
And thank you, Dr. Zhang. It's really interesting topic. And anyone has questions? Anyone has questions?
Well, can you hear me? Yeah.
Yes, please.
Yeah, the Zhang, Miss Zhang, right? I suppose. It's yeah, very interesting talk about the similarity. But the similarity really is a foundation for the turbulent modeling. If we don't have similarity, how to do the turbulent modeling? Because different places you have different spectrum. So that's I believe this is extremely important for turbulent modeling. There's a foundation for turbulent modeling. And I think that minus 503 no for the for dissipation areas looks like to me. One question is you talk about similarity in which sub range. So which sub range does what ask? Is in the inertial area or in the dissipation area? So I just asking. So do you know which subrange you have the similarity. I ask you, so you talk of similarity, right? As I said, which is subrange, yeah, but we know the common goal is very famous. Selective 5-3 is in the, I think is in the subrange of inertial area. But you talk about similarity. Are you asking in which subrange? Do you understand the question? Yeah. You talk similarity. So which, because similarity, you could have several subrange, like large scales and the middle scales and small scales. Or we talk about the dissipation subarea and inertial subarea, like a Taylor theory, something like that. But common goal of assume it is the initial subdomain, and where he assumes no viscosity, something like that. And you talk about similarity, so I just want to know, so which subrange or subdomain, you talk about the similarity. Can you understand?
Yeah. So your 50 point.
Yeah. You look at your
yeah,
I don't know which.
Professor Liu, let me try to answer your question.
Yes.
I'm Dr. Xia.
Okay.
Actually, it's in two-dimensional.
Yes.
The energy spectrum is a double cascade. But in the Liutex simulated field, we find the negative 5/3 power law. I think it's very important. Here the scaling, the initial range is near the external force scale. The external force scale is actually is the cylinder scale. I think near the range, subrange. Okay, subrange.
Oh, okay. But you go down. You know
I think Liutex simulator it's important to develop the turbulence model and turbulence city. I think it's important.
I think especially for the larger simulation, because you talk about high frequencies. I think, yeah, you can show in the go down, here. Yeah, you show somewhere, not here, down, yeah. I think up, maybe up. I don't know. I saw you some, yeah. 7. Yeah. That's you have some spectrum. So it looks like to me you are in the dissipation subdomain. It sounds to me, yeah. But this domain, it is pretty much the information missed by large eddy simulation. Large eddy simulation, because their grids is large sort of DNS that cannot resolve high frequencies or the small vortices. So therefore, this subdomain really is information you missed by large eddy simulation. So really, you cannot, get back. So you have to use a model for the subgrid vortices. But you want to model use the, use the software model. So it must be, as I said, it must be have, similarity. Otherwise, different places have different structure. And so you can how to model it. So I think this is a very particularly important turbulence theory, also given by Common Glove. He said even the larger scale are different for different cases, but the small, scales or high frequencies are similar. That's also, I think it is also part of the Common Glove hypothesis. So that your results actually show, Common Glove is correct, especially for the small length scale. So small length scale is similar. I suppose, because you didn't show many cases, especially for the channel for 2D. I know that the 2D. Some people could say, yeah, this is a 2D simulation. I understand, but really turbulence is 3D. And so, but yeah, I think some people do the 3D. The conclusion about the same. That means in the dissipation, subdomain, we really have similarity, but not the similarity for others as you show. I think you show somewhere, not for omega, not for others, not for Q, not for. So you have some way show the Liutex has similarity, not for others. So can you show that slides? I think, yeah. Can you hear me? I believe you have a slide showing the similarity only for the Liutex, not for others. So you show somewhere. I saw it. The similarity, negative 5/3. So you also showed omega or something like that, or others. The similarity, not this, the other slides. Yeah. Can you shoot go down, going down, going down, going down? Not 8, 9, going down. Yeah. 8, number 8, 9, going down. Yeah. Not this at all. Not this 10, going down. Let me see. Oh, it don't. Maybe going up. I don't know. Going up. Yeah. Maybe going up. Yeah. Going up. I see. Yeah. You have them size.
I guess page 6.
Page 6. Okay. Okay. 6. This is velocity, and the other one, not even only this. This is not this. Okay. Yeah, I saw it somewhere. Well, anyway, yeah. This new text, you have similarity. My question is, do you have similarity for other quantity? We have something like that, like, for example, we say vorticity, or Q, or omega, or others. I just asking you. So I saw somewhere where you show me, only you show us only the similarity it is for the Liutex, not for others. Yeah, that's what I say. Suppose, but from here, even for this, you say you also have some kind of similarity, some not very clear. So for the velocity. Well, common colorful, similarity.
Value, I think it's a very good comment. In the future, we try to do this.
Yeah. Okay.
Yeah. Oh, okay.
Okay. Yeah. Maybe. Yeah. Maybe go to next.
Okay, now, thanks, Dr. Liu and Dr. Xia, and thanks, Mr. Zhang. So let's welcome the next presenter, Vishwa Patel, who's from University of Texas at Arlington, and her topic is the correlation between Liutex and the shock boundary layer interaction for supersonic compression corner. Let's welcome.
You can see my screen, right?
Yes, I can. Welcome.
Yep. Good morning, good afternoon, and good evening, everyone. So my name is Vishwa Patel, and I'm the PhD student from the University of Texas at Arlington. At the end moment, I had to change my title a little bit. So I'm going to represent today on the correlation between pressure fluctuation and Liutex spectrum in boundary layer transition. The outline of my presentation will be introduction, grid and case setup, numerical methods, introduction to Liutex, analysis of the ring-like vortex structures, and conclusion. Introduction. Supersonic aircrafts are subject to high levels of pressure fluctuations, and thus intense fluctuations cause vibration, leading to structural problems. Also, it leads to total pressure loss and unsteadiness of the flow, which results in the engine failure and the rise to resistance. The pressure fluctuation in the boundary layer are very important as they are strongly correlated to noise generation in supersonic aircrafts. The flow frequency noises generated by the flow is a major issue for a wide range of engineering applications, and reducing it is challenging. Direct numerical simulation is a valuable tool that can help to overcome some of the above-mentioned difficulties with proper experimental measurements. In this study, DNS is conducted to study the pressure fluctuations and Liutex in the turbulent boundary layer. To study the mechanics of low-frequency noises, correlation of pressure fluctuation and Liutex is analyzed. The grid and case setup. So in this study, the computational domain represents the grid in the streamwise, spanwise, and normal directions, which is 1920 by 128 by 241. The stretching grid is used in a normal direction, whereas the uniform grid is in spanwise and streamwise directions. The length of the first grid interval in the normal direction at the entrance is 0.43 in the wall units. And similarly, Xin represents the distance between the leading edge and the inlet of the flat plate. Lx, Ly, and Lzin are the lengths of the computational domain in X, Y, and Z directions, respectively. The message passing interface and the streamwise domain decomposition used for the parallel computation is shown in the figure. The next will be numerical methods used. So in this study, 3D compressible Navier-Stokes equations, sixth order compact scheme is used for spatial discretization. Third order total variation diminishing, Runge-Kutta method is used for time marching, and central difference scheme to eliminate numerical oscillations. The code validation The code developed at the University of Texas at Arlington, DNS-UTA, is validated by NASA Langley and UTA researchers, is used for finding the pressure, Liutex, and vorticity. Now, introduction to Liutex. Liutex is a new physical quantity discovered by Dr. Xiaoqun Liu et al. At the University of Texas at Arlington in 2018 to describe the fluid rotation. It is a vector representing rigid rotation extracted from the fluid motion and a new defined physical quantity to describe fluid rotation or vortex. Liutex is defined as a vector which uses the real eigenvector of velocity gradient tensor as its direction and twice of local fluid angular speed as its magnitude. Del V times R, which is equal to lambda R, where lambda R is the real eigenvalue. The formula for Liutex magnitude is given as follows. R equals to omega R minus square root of omega R squared minus 4 lambda Ci square, where R is the Liutex magnitude, lambda Ci is the imaginary part of the eigenvalue, and omega represents the vorticity vector, and R is the direction of the Liutex vector. The Liutex vector is given by R equals to R times small r. The Liutex vector gradient is given as follows. The next is the Liutex core lines and isosurface figure. Liutex isosurfaces Liutex vectors on the vortex rings the vortex structures at Liutex magnitude, which is 0.05. In the closed view of the vortex rings, which is near the wall. For this study, the slices are created near the wall in the span-wise direction, and the points which are taken are some are away from the wall and some are near the wall. This is the second point, which is near the wall. The third point is again chosen near the wall. Fourth point and the eighth point, which is near, which is a bit away from the wall, but it is at the bottom. In the present case, the total of 100 snapshots are used, and the case is run with 20,000 time steps. The pressure points are chosen near the boundary layer and towards the X values, which is 680 to 720, where the vortex structures are developing. The results of correlation of 8 points is shown in the next slide. So from the correlation analysis between pressure fluctuation and Liutex, we get the point 1 has 87%, point 2 has 94%, point 3 has 96, point 4 has 96, point 5 is 80, point 6 is 92, point 7 is 96, and point 8 is 75. The points which has less than 80% of correlation, those points are away from the boundary layer and which are in the middle of the transition. Conclusion. An extremely high correlation was observed in the middle and the lower boundary layer positions. The low frequency noises caused by pressure fluctuation is observed as mainly dominated by the vortex structures or the spectrum of Liutex. The vortex rings are weakened because of the decrease in the pressure gradient between upstream and downstream. By the correlation analysis, the pressure fluctuation is closely related with the Liutex. The frequency of pressure fluctuation is same as the Liutex frequencies. Some of the references which I have taken figures from. Thank you. Any questions?
Thank you, Wishwa. Anyone has questions?
And
Oh,
let me see. If he's here, if he's here, if he
Yes, I think he was here.
here, if he's here, yeah. I think in your talk, you should tell the people what means correlation. How do you get this correlation? If he's here,
yes, I'm
but
here.
you should show. Yeah, if he doesn't show, you should show. You didn't show any formula. So what means correlation? How to get a correlation? So then people don't know what they talk about. So you have slides on your hand. Well, you did. Yeah.
Okay. Yes.
I think other people who really don't know what they talk about.
Yeah.
You have? Yeah.
I can open my paper.
Yeah. That's said. But I know you did different things. You did what you did is for the correlation between Liutex and vorticity or something like that. Otherwise, people don't understand what talk about the correlation. What you did or something. You don't have any, slides about this.
Can you see?
We can see your screen, yeah, but not the formula. Yeah.
Okay. Well, it's this one. This is
Yeah,
the correlation.
Yeah, you need to show people how to get the definition correlation, how to get a correlation. How to this you need to show the people at least. Yeah. This is a correlation, right?
Yeah, this is correlation. Yeah, the code is
the convolution, right?
Yeah.
Okay. Then you give the more definition. I think starting from beginning. Right?
Beginning the
right. You should start.
The sample mean, right? So we first have sample
right.
mean. Not this mean, not sample mean. It's mean the average, and we have the variance. And we have the
variety. Okay.
Yeah, variance, and we have the standard deviation. And this is covariance. No, I rush. It's the typo. This is covariance. The expectation of x minus ex times y minus ey. After getting covariance, we have the correlation coefficient. The covariance divided by standard deviation of x times standard deviation of y.
So yeah, it's the same formula, but in your case, you talk about like what is it? Something like that, Liutex or Q or something like lambda 2 lambda ci, something like that. But here you talk about the Liutex and pressure fluctuation. right? That's
Yeah,
my
yeah, yeah.
understanding. Yeah.
Yeah,
So,
yes, yes.
yeah, just change X and Y.
Yeah,
So
yeah,
the
yeah.
formula will be the same. Yeah,
Yeah,
it
yeah.
will be the same.
Yes,
Mhm.
it's the same. Yes.
Yeah. So, but yeah, the problem is you didn't talk in the presentation, so people may don't understand. I think the correlation really studied by other people like Yonghua Yan, yeah, and Dong. I think the session chair. I think Dong also did, but what she did is about the shock nail interaction, right? But here it is not. This is well, the title is wrong. Title no, this is old title, but the the new title is studied the correlation between the Liutex and the pressure fluctuation in boundary nail transition. So not the SBIR, not a shock boundary nail interaction. The originally, I think Dr. Yan, Yonghua Yan, and Dr. Dong talk about the shock boundary nail interaction. I think originally Dr. Dong talked, that's a few years ago, I think. It is a
Yeah.
correlation between, right, between the, omega actually. At that time, you talk about the omega, but now you don't use omega, where you use the, I think you use the Liutex. So that's similar. Well, does everything similar, just like the similarity talked before. And this time talk about the correlation between the Liutex and the pressure. So that's why I say, yeah, I think I talk too much, but because her talk is very simple, maybe people don't understand that what I talk about. Yeah. If I believe this is a important finding, and what we say that we all know where the noise come from. Right? We all know that all the noise, come from. Yeah, the reason simple, everybody knows, it's too noisy, too chaotic. The noise come from turbulence, no matter where it is, no matter in hydrodynamics, aerodynamics, aircraft. Most of the time, the noise comes from the turbulence. So know that what means noise? Noise means pressure fluctuation, because your ear can hear is a pressure fluctuation. When you have pressure fluctuation, you can hear the sound. Sound really, or sound, of course, sound is a wave. It is not direct particle. But the wave really, it is also very small sound pressure. Why the pressure fluctuation correlate with Liutex? Because turbulence is dominant by Liutex. If not turbulence, not Liutex, is not turbulence. So that's the reason we want to study this problem, this question. So we need to find the noise source, where it come from. Yeah, we know it come from pressure fluctuation. Then we know this come from turbulence. So why turbulence? Because turbulence has not Liutex. Liutex is strong. Without the Liutex, without turbulence, without noise. So that's my understanding is that. Okay. Okay. Thank you. Thank you.
Thank you, Dr. Liu. And the last presentation, the name is interactions between shedding vortices and streamwise vortices induced by a normal flat plate and delta flat plate couple, a numerical study. And the presentation will given by Vivek Nair. Because she has some physical reasons. So, Yifei Yu, Dr. Yifei Yu will do the presentation for her. So let's welcome Yifei. Can you share your screen?
Yes, thank you, Dr. Dong. Okay, let me share the screen. Yeah, can you see my slides?
Yes.
Okay, so this presentation was originally by Dr. Vivek Nail, but he does not feel well today, and his voice has gone. So I will present this slides for him. Okay. Hi everyone. Our topic is interactions between stringwise vortices and the shading vortices induced by a normal flat plate, the delta flat plate couple, numerical method. Fluid body interaction are observed across a wide range of Reynolds number regions. As an example, we have several images here. The image A is an image of a winged mile, and it is an example of a large moving object. And the figure B is a building, right, which is large static object. And we have a fish. We see a fish in the figure C, which is a moving slender body. And there is an alligator in the figure D. Well, I mean, alligator is a moving rough body, right? So what is common across all the objects shown here is the creation of interaction vertical structures, either due to passive interaction with the flow, like in the case of the building, or active interaction with the flow, like in the case of the windmill, fish, and alligator. These are the vertical interaction induced by each of these bodies. You will see that they are mostly interactions between two types of vortices, stable stringwise vortices and anti-parallel shading vortices. And in most cases, the anti-parallel angle is 90 degrees. Nice. So this is an area of interest across a diverse field. A is an example you can see here, which is a study in biological motion and propulsion, and a study in engineering, specifically the heat island effect. Right? The figure on the right shows the effect of the heat island effect. And therefore, any new insight into this interaction carries a lot of weight. So, and the motivation of our study is vortex interaction are observed across large Reynolds number regions in nature, and the vortex interactions transfer mass and energy across large distances and time scales. Understanding the mechanisms of vortex interaction has potential for flow control in the future. And the objective of our study is to study a special kind of vortex interaction induced by a solid body and producing vortices under different creation mechanism. Secondly, start vortex interaction between the stable stringwise vortex and the periodical shading spanwise vortex at Reynolds number 250. And our third goal is to the interactions induced by coupled geometry made up of two simple geometries: a normal flat plate and a delta flat plate with quartz ratio. 1. And the last study the energy transfers within the system. And the models and for the model and the simulation domain, the model consists of a delta flat plate with an angle of 20 degrees attached to the leading edge of a normal flat plate of chord length C, which is shown in figure M.1. And the plates have a thickness of 0.05 C, and the delta flat plate is a slender body with an incident angle of 65 degree, as shown in the figure M.2. And the simulation domain is shown in the figure M.3. Okay, the numerical domain dimensions. And the domain boundary condition is periodic in span-wise direction, delete boundary condition in all other directions with an inlet velocity specified for Reynolds number 250. The commercial flow solver ANSYS Fluent is used to do the computation, and most structure the hybrid mesh domain with cell count of 12 million, periodic boundary condition at the span-wise edge to simulate the infinite flat plate, and the mesh density greater than smallest common Grove scale at 250, Reynolds number 250. And last, the GIS study done for 3 different meshes at 4 million elements, 8 million elements, okay, and 12 million elements. And the circulation result is 2 different circulation magnitudes created for same flow velocity. Average vortex Reynolds number is 252 for string-wise vortex, and 3654 for shading vortices. Effective flow length of 1.3 to 1 yields an average circulation ratio of 14.5 to 1. The vortex Reynolds number equals to circulation divided by kinematic viscosity, and the effective flow length is the length of the solid body that induces the respective vortex roll up. Well, to get a better understanding or the length of interaction region, the time average circulation is calculated along the span-wise z, which is z direction, and the for the leading and the trailing edge. Well, circulation along the span in the leading edge and the trailing edge is shown in figure C.1, and the influence in the leading edge with strong effects in 2-3 span lengths from center line. The net increase in circulation is higher than the circulation of the STV. Break in LEV due to the delta flat plate solid body causes a stronger vortex roll up. And lastly, the positive influence seen in the trailing edge, as shown in figure C.2, counterintuitive, was expecting a smaller albeit opposite trend. In figure C, it shows the LEV and STV rotate in the same direction, which is the constructive interaction expected while the TEV and STV rotate opposite directions. Okay, and so before moving forward, it's important to talk about our traditional methodology employed for calculating quantities within a vortex or vertical structure. For example, if we are calculating circulation, we are taking the area integral of vorticity within a planar surface of interest, and the methodology for that is is to create a bounding box and or scalar stretch holding value and or stretch holding through vortex identification method. Usually we use Q criterion and lambda 2 criterion, and the next carry out the calculation. Okay, so and what's the limitations of the previous methodology? Firstly, human visual input required, or all techniques require some form of guesstimation. Guesstimation means guess and estimation. Well, that's an informal word. You cannot find this word in the vocabulary. And the second drawback is it is prone to biases. That means pretty pictures looks pretty. Well, I think you all heard some of the jokes that the CFD represents for colorful fluid dynamics, right? So some people think the CFD the purpose of CFD is to draw colorful figures, and this could be a question whether the pretty pictures reflect the real structure of vortex, right? So we don't know, so it's a question. And the third drawback is higher order vortex identification methods are time consuming and require experience to understand the results. This is especially true of lambda 2 type identifier. Okay, we can see the movie. Okay. Next, additionally, the traditional methodology is slow because it requires an iterative approach, which can take hours if it's a well-studied phenomena and the vertical structure is known appropriate. Um, okay, all days trying to it's yeah, it may also take days trying to validate the vortex identification qualification if it is a new flow phenomenon being studied. Now engineering like tools that will cut down on time and the cost and make certain processes simpler. And for vortex identification, the Liutex method does just that. It's the right? It's the third. Okay, it's the third days of the workshop, so I'm sure by now every one has some understanding of the algorithm. So I will be focusing on the application advantages of Liutex method. Its two biggest advantages are it is quick and can be easily applied to raw flow data easily, and most importantly, it removes human intervention. So here is some features of the traditional method and the Liutex method. The the extremely important advantage of Liutex method, it removes human intervention. It does not have it's not prone to biases. Okay, and using you can see here how straightforward the methodology for applying and use the Liutex method, and the flow structure are well defined and in strong agreement with experimental observations. Okay, so we first define bounding box, then calculate Liutex method. Then we can draw the isosurface of Liutex vector, and then we finish the process. Oh, okay. Let's see the move. Okay, so we use the Liutex method, calculate the magnitude of Liutex vector, and use it as a threshold for all calculations of circulation and vorticity. Here we have the average span-wise and the string-wise vorticities in the C.4 in the figure C.4, and the string-wise direction. And the span-wise direction in figure C.5. Okay. So what we can observe is the negative Z vorticity is the strongest near the solid body, and the observation consistent with literature. Asymmetry in the Okay, asymmetry in Z vorticity intensity, where X vorticity is symmetric. Net increase in VEZ vorticity is not proportional to net X vorticity. Mission value is Y vorticity, and asymmetric in Z vorticity intensity, while X vorticity is symmetric. Negative Z vorticity intensity does not drop along the span, indicative of LEV generation being strongly affected by string-wise vortex cutoff. To better understand the interaction, we divide the domain into 3 regions in the string-wise X direction, and we can find near the near field. Okay, so the near field is the region with strongest vorticity observed, and the intermediate field is the region adjacent to the strongest vorticity region, which is near field with decreasing trends. And for the far field, is the region exhibiting asymptotic trends, and the energy fluxes are spatially averaged and recorded as a function of time. The interaction between the string-wise and the span-wise vortices creates vorticity in the cross string-wise direction Y, and this quantified by calculating the Y entropy in all planar directions for the near field region. The Y entropy in Z clearly shows a unstable mixing region at the center and not extending more than 1 chord length in either direction. The Y entropy in X shows a periodic increase and decrease of
We cannot hear you.
1/10 the shedding frequency. Okay, for the intermediate field, we observe that the intensity has decreased drastically, and that no mixing intensity pattern are observed for any of the domains. And so we can state that all mixing interaction between the string-wise and span-wise vortex occurs within the near field. Okay, the future work we can do is we can conduct a vorticity transport analysis, and then we can conduct a spectral analysis. Also, we can run a parametric study. Okay, thank you for your attention.
Thank you, Dr. Yu. Anyone has questions? Okay, I have a question. Can you introduce more about inflow condition? Because
Inflow condition, I think it's
because you're
here.
talking about the shading vortices, right? Shading vortices used by two flat plate.
Inflow condition.
I mean the Mach number or the velocity of the inflow bounding.
I only helped him use the method of Liutex, and I don't know how did he set up his case.
Let me explain a little bit because this work done by the student in the mechanical engineering. Which,
feedback.
Yes, Vivek Leo, and I as the committee member of his PhD committee. So really, he just send as an email say he was sick. He cannot speak well, so because the catch cold. And so I just ask if he to help him to present. Really, if he cannot explain too much, it's so unfortunately, I just said, well, he just read his slide. He made a slide, so. That's I believe he's pretty much his PhD dissertation because he said he will get difference next week. He just sent me email, but unfortunately he was sick.
And I have another question.
Yes.
So I don't quite understand what is bounding box. Bounding box, what's that?
Bounding box, well, bounding box. Well, from my understanding, I think he means bounding box before with bounding box. I think it's maybe another way to say the domain, create the domain. So that's my understanding, but very easy.
Computation domain, maybe.
Yeah.
Oh, okay. Okay. Thank you, Dr. Yu.
You're welcome.
Okay. So thank you all. It's time to close section 9, and the next section will start after 10 minutes break. And Dr. Yonghua Yan will be the host. See you. Thank you.
我不是讲个意思，就是会还是照开，开完了那就是算那把我们把那 window 关掉，然后的话呢，重开个 window。Yeah, sorry. Yeah.
Excuse me, Dr. Liu.
Sorry. Yeah.
Can you turn off your microphone?
Hello.
Hello, everyone. Can you hear me? Hello?
Yes, we can hear you.
Oh, okay. Good morning, good afternoon, and good evening. Okay, so now we will have our second session in this morning. My name is Yonghua Yan. I will be the host. Okay, and our first talk will be given by Songtao Chen from Shanghai Jiao Tong University. His title is identification of vertical structures of flows around a surface passing finite square cylinder with rounded corners. Let's welcome Songtao Chen.
Can you see my screen and hear my voice?
Yes.
Okay.
Let's go ahead.
Start. Hello, everyone. My name is Songtao Chen. I'm a PhD student at Shanghai Jiao Tong University, and my supervisor is Professor Decheng Wang. There has some change with my title. Today, the topic of my presentation is the identification of vertical structures of block bodies in ocean environment. My presentation is divided into 4 parts: background, numerical method, result and discussion, and finally the conclusion. First, let's see the background. As we know, the ocean environment includes many complex conditions. In marine hydrodynamics, we mainly focus on the currents, waves, and combined wave current conditions. Today, I will only talk about the first 2 conditions, currents and waves. As for the wave current condition, it's still under our research. And so in the above mentioned sea condition, the marine structures are our research. As you can see in the following picture, the cylinder is typical structure of many offshore platforms. The left one is a semi-submersible. It consists of 8 circular columns. The middle one is a model of FPSO. Its basic structure is a cylinder. And the right one is the foundations of wind turbines. In the ocean environment, these structures involve many phenomena like vortex-induced motion, VIM, and wave structure interaction, WSI, and so on. In today's presentation, I will present 2 cases. The first one is the flow around a finished surface piercing cylinder, and the second one is the Fox wave interaction with a finished cylinder. Next, I will introduce the numerical method briefly. As you can see, for the governing equation, the flow is described by the 2-phase incompressible Navier-Stokes equations. The continuity and the momentum equation are shown in this slide. I'm sure you are familiar with these equations. However, in the second case, we adopt the ghost free method to handle free surface jump condition in large density ratio air-water flows. It can eliminate the superior air velocities, near the free surface. And therefore, the velocity field can be improved for the following analysis. After using the ghost fluid method, the form of the momentum equation changed. The density is only in the pressure gradient term. And besides, we also implement special numerical schemes to handle the free surface jump conditions, like the picture shows. If you are interested in it, you can see the reference by Yasaka in this paper. So, as for the turbulence model, we adopt the SST-DDES method. It is a hybrid RANS LES method, so it can achieve the high fidelity of the flow field compared with the RANS and improve computational efficiency compared with the LES. The transport equation are given below. To capture the free surface accurately, we use a geometry Wolf method. It is based on the piecewise linear interface calculation, PLIC. It is based on the, recently it is implemented in OpenFOAM version 8. And the basic procedure is shown in this flow chart, and the right figure shows the schematic of a typical cutting plan, as the gray part shows. In general, in this method, it can prove the accuracy compared with the original interface compression algebraic method, and also ensure the robustness for the practical engineering problems. In our study, we mainly use the normalized omega Liutex method to identify the vertical structure. Since this method has been introduced by many others, I will not spend much time to introduce it again. Here, I just want to emphasize that the B0 in this small parameter is recommended to be 10 to the power of -6 in Murray hydrodynamics. This value is based on a sensitive study by Dr. Zhao in these references. If you are interested, you can see these references. Next, I will show our results about the vertical structures. The first case is the flow around a finite surface pairing cylinder. The Reynolds number is 270,000, and the Froude number is 1.1. The computational model is presented in the upper left figure. The diameter of the cylinder is 0.2 meters. The aspect ratio is 6, and the draft ratio is 4. The right figures are the structured computational mesh. The total number is about 15 million, and the maximum Y plus is below 1 during simulation. The regions near the weak region and near the free end are locally refined. So first, let's see the animation of the free surface. You can see a way run up in front of the cylinder and a depression region behind the cylinder, and the surface deformation is very violent. Before analyzing the vertical structures, I first present the validations with the experiments. Here is the surface elevation contour lines. The upper is the experimental measurement, and the lower is our CFD results. As you can see, our CFD result is in good agreement with the experiment. To validate our results, we also take two slices. One slice is the symmetry plane, and the slice 2 is y divided d equals 1. As seen in the upper figures, the result of these two slices match well with the experiment. The dot represents the experimental measurements. I also present compression of the time average velocity at two different depths, one near the free surface and one near the free end. In the experiment, the velocity field is measured with the PIV technique. We can see the recirculation zone represented by the blue region captured well in our simulations. So next, let's turn to the vertical structures. In this slide, I show the side view of instantaneous vertical structures. Here we use the isosurface of omega r equals 0.52. In figure A, we can see some large scales in the weak region. They are the most common vortex shedding in the flow around cylinder. In figure B, we focus on this region, the region near the free end. We can see a curved surface. It represents the recirculation zone, and we can also see many small scale vortices attached behind it. Next is the top view. We can observe many small scale wave-induced vorticities in the weak region. These vertical structures are caused by the violent surface deformation as shown in the animation. And they cover quite a large area, even in the far field. You can see represented by the light blue structures. In front of the cylinder, we can also identify some necklace vortices, or also called horseshoe vortices. In figure D, we can further see these structures are slender and surround the cylinder. Next, we use time average field to show the primary structures in this flow. To exclude some weak vortices, we increase the threshold to 0.65. Here, the upper part of the cylinder is presented first. The isosurfaces are colored by the streamwise vorticity, and the light blue surface represents the interface between the air and the water. In front of the cylinder, we can see a complete necklace vortex, and behind the cylinder, we surprisingly find a pair of counter-rotating vortices attached to the cylinder surface. We term it the wave-induced vortex. It is probably caused by the strong wave motion behind it. Besides the isosurfaces, we also use the Liutex lines. As shown in the left figure, Dr. Gao used the Liutex lines to analyze the hairpin vortices in a turbulent channel flow. We apply the same method to the necklace vortex. The Liutex lines reveal that the local rotational axis is tangent to the cylinder only near the front stagnation point. You can see here, only tangent. And when it travels further downstream, it quickly becomes like spiral. We think this phenomenon will explain the dissipation of the necklace vortex downstream. Similarly, we also use the Liutex vectors. As you can see, the vectors are all tangent to the isosurface. Then we focus on the lower part of cylinder. Here, the threshold is further increased to 0.85 because the flow around free end is very strong and complicated. The isosurface is colored by the time average string vorticity. In figure A, we can first see a pair of counter-rotating arch vortices attached to the leeward side of the cylinder, and they incline upward with the strong upward flow. In figure B, we can see two pair of counter-rotating tip vortices, namely the T1 and T2. And in addition, we find a small structure colored green, AB. Actually, we think it connects the arch vortices near the edge. Then we present the time average streamlines at different slices around tip vortex TVL1. We can see the isosurface is across the course of streamlines at each slices. In the right figure, we also present Liutex lines. The blue arrow here indicates the primary direction of the rotational axis, and the red arrow show the detailed behavior of the twisted Liutex lines. When the tip vortex originates from the cylinder, it's kept straight and tangent to the cylinder. Then it quickly becomes spiral. Here you can see here. And it is similar to the necklace vortex we introduced above. Then let's come to the second case. It is a Fox wave interaction. with a finished cylinder. The computational model is presented in the left figure. The diameter of the cylinder is 0.3 meters, and the diameter of the cylinder is 0.15 meters. The computational mesh is shown in the right figure. The total number of the structure mesh is about 6 million, and the region near the free surface is locally refined. For the Fuchs wave group, we use new wave theory to generate it, and the wave crest amplitude is about 0.1 meters. And I also should to notice that we use the ghost fluid method in this case to animate the superior velocity in the wave cases. Then let's see the animation of the wave crest. We can see evident wave crest pass through the cylinder. Let's see it again. It is the wave crest. You can see. Oh no, it is the wave crest pass through the cylinder. First, we still compare our results with the experiments. In the left figure, the time history of wave run-up height are compared. We can see our prediction is in good agreement with experimental measurement and the numerical results by others. And in the right figure, we compare the pressure of a probe. As the picture shows, this probe is at the front of the cylinder and 0.05 meters below the still water. The comparison shows our numerical model can accurately predict the pressure. So after validating our solver, let's come to the vertical structure in this flow. Because we are still analyzing this case, we only show the result during the wave run-up. They are the animations of the instantaneous vertical structures. We provide two different views. One is side view, and the other one is the front view. And then the magnitude of Liutex is used here for isosurfaces. As for, I'm not still using the normalized omega Liutex method. I will explain it later. It seems slow. In this slide, we choose 3 time instants for analysis. In the left figures, we can identify 3 obvious vortices, N1, N2, and N3. The N1 is possibly caused by the circular motion of the water particles. And the N2 and N3 are generated by the interaction between the flow and the free end. When the wave elevation increases, the figures in the middle. The N1 is disappear. As for the N2 and N3, they gradually increase in size and move upward. In addition, 2 additional vertical structures, N4 and N5, occur at the edge of the free end. It indicates that the flow near the free end is strong and complicated. When it comes to the maximum run-up height, let's see the right figures. All vertical structures have large deformation, especially the N2. It behaves like a symbol omega. In this slide, we compare 3 vortex identification methods. For the Q criterion, even when we increase the threshold to 1000, a very large value, we can also see the shear contamination on the cylinder surface. As for the omega method, it also gave unwanted structures near the free surface. As the red rectangle shows, it is caused by the wave motion itself, because wave motion, it is a circular motion. Even when we increase to 0.7, it also will show some part of it. However, for the Liutex, it gives the best results. No shear contamination and no unwanted structures caused by the wave motion. So we strongly recommend using the Liutex method for the wave structure interaction cases. Finally, it's the conclusion of today's presentation. Finally, the omega Liutex method is capable of capturing typical structures in the flow around bluff bodies. And secondly, the Liutex vectors lines can well indicate the local rotational axis. we think it helps a lot in understanding the flow mechanism. So finally, we strongly recommend using the Liutex method for the wave structure interaction cases. And that's all for my presentation. Thank you.
Okay, thank you. Thank you for your presentation. Is there any question? Any question?
Well, if nobody have question, I have some question. First, well, it's a very impressive talk. I think very impressive work, actually. So
Thank you, Professor Liu.
Yeah. So first, I have some questions. Is 20? Let me see. Well, you're about the
29?
color. Color. I'm 28. Is it 28? Is that yeah?
28.
The 28 slides. Yeah. Slide 28. Yeah.
Sorry.
You cannot show.
Okay.
Yeah.
This slide.
Yes. No, I just showed the 28.
Yeah, show the slide.
Yeah, this is.
Yeah, 28.
Yeah,
yeah. I guess. So your color is the vorticity, right?
Yeah, streamwise vorticity. We want to show the direction of these structures.
It's a vorticity. Well, because when we talk, you still use isosurface. Isosurface should be same color. So you use different color. That means you didn't. It's not a Liutex. Liutex should be the same. Yeah. It's a vorticity.
Yeah. I use the isosurfaces for the Liutex magnitude.
Yeah, but this is also, I think you show us that's later, right? You say the Q looks like a shear contamination. Go down. Yeah, here, right, yeah. So the Q looks like, but did you check, use different threshold for Q?
Yeah, I check it. Yeah. 1000 is a very large value in this case. You can see the structures is very small and the contamination still appears.
Okay. So if you reduce the threshold, it will get worse. Is correct?
Yeah.
So
I don't show here.
Case, okay. Yeah, it didn't show you, but it sounds to me your conclusion is the Liutex is better than the omega Liutex, right? Than the Liutex omega. This is not omega. Really, it's Liutex omega. So Liutex self, is even better. Something like that. Your conclusion is like that. Yeah. But also go up, going up. Going up. I think you use the Liutex 9s. I think you use Liutex 9s and the streamline. Streamline. Streamline and Liutex 9. Yeah, you have one.
Yeah, here.
Yeah, I see. Not this. I think possibly down or up. You have both Liutex 9 and
streamline.
Streamline. Yeah, like this. Yeah, this is well, this is a pretty new and impressive because most of the people, or almost everybody, use the isosurface. But this Liutex 9 is not isosurface. It is similar to tubes or lines, something like that. It is really very few people use that. But you cannot use a Q line. It's not Q line, right? You only have vorticity line or Liutex line. Because vorticity is also the vector. But I don't think you can use vorticity line. We are not give anything. But you cannot use Q line or lambda 2 line or lambda CI line. You cannot use that. But you use the Liutex line. Well, this is always a question bothers me. Why we use the isosurface for the vortex structure? It looks like this is pretty new. So use the Liutex 9 to show the vortex structure. And
yeah,
when
I
it comes,
actually follow the work of Dr. Gao in hairpin vortices. I read these references to apply the same method to my study.
Yeah, that's a vorticity line. We know the left. Yeah, vorticity line is doesn't coincide with the Vortex structure. Yeah, but I think Liutex line, it is agreed to the Vortex structure. So that's raise a question. Why we use the isosurface Liutex? Why you don't use the vector like Liutex lines? Well, this is just a question. People could think about that. I think this is very impressive. Where you use both streamline and a Liutex line. I think, yeah. Okay, that's my talk. Let me and then the other people maybe ask questions.
Thank you,
okay,
Professor.
Thank you very much. Yeah.
Okay, thank you. But maybe we don't have enough time now. We can, have more questions later. Okay.
Okay.
So our next speaker is Yunpeng Ma from Shanghai Jiao Tong University, and his topic is identification of vortex around high-speed shape by Liutex method. Let's welcome Yunpeng Ma. We cannot hear you. Hello, we cannot hear you.
Hello, everyone.
Now we can hear you. Yeah, go ahead.
Hello, everyone. I'm great honor to share with you some recent learning of the third generation vortexes identification method. The research object of my presentation is changed to the polar shape, polar cruise shape. So the title should be the identification of vortex around the polar cruise shape based on the Liutex method. The content of my report is mainly divided into the following parts: the numerical methods, the shape model parameter, and the setting up, and so on. First of all, please allow me to introduce the Noiform solver. The Noiform solver is a software which is independently developed by our team, the Shanghai Jiao Tong University Computational Marine Hydrodynamics Lab, which is used for the calculation of the hydrodynamics of ships and marine engineering. Its governing equation is incompressible average Reynolds equation. That will be the RAS. The turbulence model is the kick omega 2 equation model. The VUF method combined with artificial compression technology is used to capture the free surface. The PISO or the PISO method is used to calculate the pressure and velocity. Our object is polar cruise ship number 1, which is built by the Chinese Merchant Industry Holding Corporation Ltd. In December 2019. The views of polar cruise ships in all directions are shown in this figure. The superstructure of this polar cruise ship is tall, and the bow of shape is a kind of a special one. The specific parameters of the shape are shown in this table. For this calculation example, the resistance of the shape in still water is calculated. The speed is set to 11 knots and 30 knots respectively. the calculation domain, someone also named it the calculation field or region, is set up as shown in this figure. We adopt half domain calculation. The origin point is the interaction point of the bow and the free surface. The distance from the origin point to the inlet is the length of the shape. The to outlet is 4 times. To the bottom is 1, and to the top is half of the length, and to the side is 1.5. The mesh is shown in this figure. Since the still water resistance is calculated when we set up the mesh, so we pay attention to refine the free surface and the hull. The total mesh would be 4 million. In order to analyze the vortex distribution in the field, the longitudinal and transverse cross section are made. The position are shown in this figure. There are 5 sections in total. There are 3 in the y equals 0, 0.27, 0.52, and section x equal 3.5 and x equal 8. For the 11 knots, for the vortexes of the transverse section, x equal 3.5, as shown in the figure. For the first generation vorticity method, because it's severely affected by shear pollution, it cannot accurately identify the vortexes. For the second generation Q method, it's also affected by the shear pollution, but not as much as the vorticity. For the Liutex and omega R, the position of the main vortexes are familiar. For the section, for this section of the closed shape, the vortexes by Liutex method is easier to distinguish than the strong and weakness. For the transverse section, x equals 8, which is located behind the stern. The strength of vortexes is small, and the distribution of the vortexes are identified by a different method as different. There is nothing similar. For the longitude section y equals 0. The first generation vorticity method again failed to identify the vortexes due to the sharing pollution. For the others, the vortexes are distributed in similar location. For the vortexes, which is far away from the stern, they can be identified by the Liutex method, and some of them can the omega R method can also figure it out. For the longitudinal section, where equals 0.27 and 0.52. For the Liutex and the omega R, the distribution of the vortexes is similar. On this section, the distribution of the vortexes and the distinction between strength and weakness, the result of the Liutex. The result of the Liutex would be better. These are the isosurface of vortexes are identified by each method. On the side of the shape, there are vortexes distributed along the wheels generated by the hull, and there are also vortexes along the longitudinal section behind the stern. For ships sailing at 11 knots without the propeller, there are 2 main wheel-making airs, the bow and the stern. So we can see the vortexes caused by the bow and stern wheels should be the strong vortexes, and the vortexes in the longitudinal plane behind the stern should be the weaker one. The vorticity method, as one can see, is affected by the sharing, and it's unable to identify the vortexes correctly. For the Q method, it's also affected by sharing, especially the bottom of the bow. More complete isosurface of vortexes on the side can be identified by the Liutex method. And what's more, for the vortexes near the ship, especially on the bottom of the bow, the Liutex method would be better. Not only can be affected by the sharing, but also can better show the isosurface, but show the structure of the isosurface of the vortex. The omega method can figure out some of the vortexes on the side. What's more, it identify details on the vortexes behind the ship's stern. So the omega R for this, of course, for this calculation, it's powerful to identify the weak vortexes behind the stern. This would be the 13 knots. In this section, X equal 0.5. The vortex identification is similar to that of the 11 knots. When the X equals 8, the distribution of the vortexes near the ship are identified by Q, omega, Liutex are similar. Now this is different from the case 11 knots, for which there's nothing similar. For the longitudinal section, y equals 0.27 and 0.52. The vortexes identification situation is similar to that of the 11 knots. What's more, from the picture, the vortexes near the hull are identified better by the Liutex method. The distribution is similar, so we can, from the result of the Liutex, we can distinguish the strengths between the weakness clearly. And these are the isosurface of the vortexes identified by a different method in the case of 13. They are similar to the previous case. The omega R method can identify more details of the vortexes behind the ship's stern. It can also identify some of the vortexes on the side of the ship, complete isosurface of the vortexes on the side, and near the ship can be identified by the Liutex. As the conclusion, the resistance of the polar shape in still water is calculated using the node form solver, and we use the Liutex omega R to identify the calculation results for vortexes distributed along the wheels and behind the stern. The vorticity and Q method is affected by the sharing of the fluid, especially the vorticity is unable to identify the vortexes correctly. The omega R and the Liutex are seldom affected by this sharing. The omega R method for this calculation is powerful to figure out the details of the vortexes behind the ship's stern. And for the vortexes on the side and near the cruise ships, the Liutex method can show us more complete iso surface of the vortexes. Sir, this is my presentation. Thank you.
Okay, thank you. We have 3 minutes, so I think that's good for at least one question. So any question?
Yeah, let me say with. Look at your results. I think I don't know which page. Yeah, this is fine. Yeah, 23. 23 or yeah, it is fine, I think. Yeah. It sounds to me what is it is not very good. That sounds to me.
Yeah.
Q is okay, but it compare with Liutex, yeah, omega is okay. But for the Liutex, looks like a structure similar to the Q, but Q some kind of red area is shared, right? My understanding, right? Yeah.
Yeah.
So that means Q still have share contaminant.
Yeah.
And compare with Liutex and omega Liutex, there's some difference because in the wake, you have more structure by Liutex omega and less structure by the Liutex. Is it correct? Yeah, so Liutex, omega and Liutex may be better for complex structure with strong and weak vortices. Is correct my understanding? Yeah, because you catch some weak vortex structure, but Liutex did that. Is correct? Yeah, my understanding is correct. Yeah, okay. Yeah, that sounds to me. Yeah, it sounds to me. Compare with the four method here, what is it actually is cannot be used. And it sounds to me it cannot be used. And Q can, but get a basic strong vortex structure, but still have share. And Liutex is not share, but cannot capture the weak. Of course, you use isolate weak vortex structure, but Liutex omega method you catch both strong and weak, vortices. But meanwhile, I'm not sure you have noise or not noise. It sounds to me that's still needed to be studied. That's my understanding. Okay.
Okay. Thank you.
Yeah. Thank you. Good work. Well, nice work.
Okay. Our next speaker is Shan Trio from the University of Texas at Arlington. Her topic is Liutex and DMD analyzing coherent structure in turbulent flow after micro vortex generator. Let's welcome Shan.
Can everybody hear me?
Yes, we can hear you.
Hi, everybody. My name is Song Chu. I'm from the University of Texas at Arlington, from Department of Mathematics. My topic today is the Liutex and dynamic mode decomposition analysis of coherent structure in the wake of micro-vortex generator. First, we go to the constant. We have the introduction, approaches, or Liutex and third generation of vortex identification methods, dynamic mode decomposition, DMD, and the last one is conclusion. This is the flow transition. For flow transition, we have laminar boundary layer, transition region, turbulent boundary layer. For my research area, I only focus on the turbulent boundary layer. It's right here, where they had a shock and they had a separation bubble. Boundary layer is approximately 99% of velocity of the free stream. Next, we go to introduction of the vortex. Vortex is the rotation motion of the flow. Vortex, they exist everywhere in the nature. For example, on the cup of the coffee, you can see like right here, you can see the vortex. Or you can see the vortex on the whirlpool, or when the airline take off or land it. You can see this one, the vortex. For so many years, the people believe vortex is vorticity, and vorticity can calculate rotation. However, we easy to find counterexample. In laminar boundary layer flow, there is no rotation and vorticity is non-zero. It means vorticity cannot express the rotation and vortex is not vorticity. In this case, magnitude of Liutex is zero everywhere. This is the video about numerical clearance at the central plane of the compression ramp control. We had a micro vortex generator right here. It generates the vortex ring. They will draw the shock. Let's see the shock. And reduce the separation bubble right here. Next, we go to introduction to the micro vortex generator. This is the figure configuration domain of the ramp and micro vortex generator. We had a micro vortex generator right here. And in my research area, I will choose this area right here to analyzing my data. Because in this area, they had a shock and they had a separation bubble region in here. And this is the figure of geometry of micro vortex generator. On my research, I choose the Mach number equal 2.5 and Reynolds number equal to 5760. The height of MVT 1/2 the height of boundary layer. The height of the micro vortex generator equal to 4 and alpha equal 24 degrees. And C is the jaw plane is 7.2 the height, and S is the distance between the micro vortex generator, S equals 7.5 the height, and Z is on the corner. We had trim wide span one normal divided by 1600 by 192 by 137 is the gig of the system, where X is span wide, Y is normal, and Z is trim wide direction. Next, we go to introduction to the micro vortex generator. This is the figure of 3 types of micro vortex generator. First one, we got the forward and the backward facing wax orange. The second one, type B, we call counter and roll, co-rotating vents. And type C, we have wishbone and double tie Wheeler vents. On my research area, I just used type A, the first one, the forward ones. Micro vortex generator is the low passive control, reducing drag, elevating separation, enhancing the quality of velocity profile. The benefit is simple design, easy implement, low cost, and robust performance. Next, we go to application of micro vortex generator. Micro vortex generator we use mainly in the air intake of the jet engines in the modern military aircraft. Next, we go to the Liutex and third generation. Vortex were proposed by Dr. Chao Kun Liu and his researcher in 2018. In 2019, the name they were named Liutex. The Liutex is present the local British rotation part, scalar, vector, tensor form with the shear contaminant. Liutex were defined by the magnitude big R and small vector I eigenvector of velocity radiant tensor or local rotation axis. For physics formula, we had this formula. For mathematics formula, we had this formula. When we combine these two formulas together, we come up to the new formula, which means small vector r and lambda r is real eigenvector and eigenvalue of velocity radiant tensor. In 2019, Dr. Wang come up with a new formula to calculate the magnitude of Liutex. So the magnitude of the Liutex was defined by the dot product of the small omega and small vector r minus the square root of the dot product of omega and r squared minus 4 lambda ci squared, where the dot product of omega and r is magnitude of velocity in direction of r. The square root of the whole thing is the pull shear part. The small omega vector omega is local vorticity vector. Vectors small r is eigenvector of velocity radiant tensor, local rotation axis, and lambda ci is imaginary part of complex eigenvalue of velocity radiant tensor. Advantages of Liutex. Liutex is local accurate unit and Gaussian invariance. Liutex has its own scalar, vector, and tensor form. Liutex provides accurate quantity to represent the absolute vortex rotation strength, whereas most of the vortex identification methods could be contaminated by shear. Next, we go to dynamic mode decomposition (DMD) methods. First, we go to introduction of DMD. Smith and his researcher will introduce DMD by using numerical and experimental data to extract dynamic mode in 2010. Abu and Young applied the dynamic mode algorithm to extract the wide range of the structure in 2011. John and Amit use the dynamic mode decomposition to approximate coherent structure with three topics: model, decomposition, and model reduction in 2019. Next, we go to DMD. First, we had P matrix with m by n. So from P matrix, we got the X matrix by m by n minus 1. We got like the column from x1 to xn minus 1. After that, we had from P matrix, we got the X prime matrix by n minus 1. It starts from x2 to xn. So x prime will approximate equal to ax, where a is linear operator relating to Koopman operator. So we got xk plus 1 equal to phi sigma kb, where b is the sigma inverse x1. Sigma is the diagonal matrix where all the element is 0 except on the one in diagonal. And phi is n by r matrix from phi 1 to phi r. So xk plus 1 equals phi 1 lambda 1 k b1 in mode 1 plus phi2 lambda 2 kb2 in mode 2 plus blah 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 plus phi n minus 1 lambda n minus 1 kb n minus 1 in mode n minus 1. And we have lambda j equal e power wj. So xk plus 1 equal phi 1 e w1 kb1 in mode 1 plus phi 2 e to power w2 kb2 in mode 2 plus blah 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 plus phi 2 e w n minus 1 kb n minus 1 in mode n minus 1. Wj equals Cj plus or minus I dj's, where Cj is real, W row and decades, and dj is imaginary of Wj, or we call frequency. Next, we go to procedure. From the Navier-Stokes equation, Dr. Zhao Kun Liu and his researcher come up to the new code we call LES code, or called like LES-UTA. From this one, we got numerical solution. From the numerical solution, we apply the Liutex. So we had a vortex structure flow visualization. Then we had Liutex analysis on DMD. Next, we go to dynamic mode decomposition analysis of coherent structure in the web of micro-vortex generator. This is the discussion on the vortex structure of micro-vortex generator web by using Liutex as the input. This is the figure of the whole domain. And the micro-vortex generator right here. And I just use this part right here to analyzing my data. I use a DMD. The reason why I choose this region, because in this region, we will get the shock right here. And we had a separation bubble right here. And parameter of subzone, the X direction is start from 35 to 105. The Y start from 1 to 110, and the Z start from 901 to 1300. Now we had the amplitude and the frequency of 120 DMD mode. In my research area, I just take the first 10 DMD mode to analyzing my data. So you can see mode 1 had a real value and no imaginary value. And mode 1 has 0 frequency. Then we have mode 3, 5, 7, and 9 had a negative frequency. It's on the left side, which are computed from the complex conjugate of the mode 2, 4, 6, 8. And mode 3, 5, 7, 9 had the same frequency with mode 2, 4, 6, 8, but they lie on the opposite side. Next, we had a dynamic mode decomposition eigenvalue for all temporal mode in the unit circle. And we just like show the first 10 eigenvalue of DMD mode. The unit circle is show the real and imaginary part of the first 10 eigenvalue. We can see the mode 1 get only the real value. And you can see the mode 2 and mode 3, they get the same eigen value, the real eigenvalue, but they had like opposite side for the imaginary part eigenvalue. This one we got a positive eigenvalue, and the mode 3 you got negative. The same thing for mode 4, 5, 6, 7, 8, and 9. The rest of the mode lie inside the unit circle, which show the low decay rate. Only mode 1 lie on the unit circle. It shows it kind of stable. Next, we go to dynamic mode. The vortex structure, I use the isosurface of the Liutex equals 0.05 of the first 10 DMD mode. We can see the mode 1 had a smallest scale among the first 10 mode, and we had a mode 10 had a largest scale structure 1. The structure of the mode are getting a little bit larger as the mode increasing. The higher mode had a larger scale structure than lower mode. Next, we go to conclusion. Each DMD mode had a single frequency. Mode 1, stable with a high frequency, had a smaller vortex structure compared to the other mode. Mode 2 to mode 10 with the slow decay rate, having the low frequency than mode 1. Mode 7, 8, 9, 10 with lower frequency had a larger vortex structure. Mode 3, 5, 7, 9, same frequency with mode 2, 4, 6, 8, but they lie up in the opposite side. A reference, this is all the reference that I use for my talk today. And thank you.
Thank you. Is there any question? Is there any question? Okay, now it's already the time for the next speaker. So the next speaker is Xingchen Wang from Wuhan University. His topic is on the comparison of Liutex method with other vortex identification methods in a no-shaft pump jet. Okay, let's welcome.
Can you see my screen?
Yes, we can.
Mr. Chairman, distinguished professors, ladies and gentlemen, good morning, good afternoon, and good evening. This is Xingchen Wang from Wuhan University. It's a great pleasure for me to be here to address such a gathering. And today I want to present my preliminary work on Liutex investigation of flow structure and hydraulic loss in a shaftless rim-driven thruster. My presentation is mainly divided into the following 4 parts, which are resource background, computational methodology, resource and discussions, and conclusions. Merging propulsion system is a key component of a ship system, whose design is of great concern. Nowadays, there are 3 main marine propulsion systems. The most conventional one is namely conventional propulsion plant. Its propeller is connected to a shaft, which protrudes from the rear of the ship to the prime mover. And this kind of structure has several deficiencies. And firstly, the rotation of the shaft can raise significant friction power loss. Furthermore, this structure occupies a large amount of engineering space and even produce high-level noise and vibration. Subsequently, improved system is named the cordial drive propulsion plant, which is popular since the 1990s. And as the middle picture showing, the propulsion plant is ported into the ship. This structure proves to be able to account many deficiencies of the conventional one. But its port is so long and so large in diameter, which can further impact the propulsion efficiency. In recent years, a newer system, namely shaftless rim-driven thruster is popular. It's a marine propeller which doesn't require shafts for transmission of the driving torque. Therefore, it can significantly overcome the deficiencies raised by the shaft. This slide shows the geometry of the shaftless rim-driven thruster. The motor stator is installed inside the shell, and the rim functions as a motor rotor to drive the rotor blade. There is a gap between the shell and the rim, and this gap is of great concern. When the thruster is working, backflow leakage will occur inside the gap. It can greatly impact the total efficiency and the operational security. However, this gap is the size of the gap is very small, so that the local shear effect is very strong. Therefore, the common vortex identification methods such as the Q criterion performs badly. In this aspect, Liutex method can greatly eliminate the shear effect, which seems to be a promising method in understanding the complex problem of a shaftless rim-driven thruster. To testify the ability of a Liutex method, in such a case, we conducted a preliminary numerical study. Or numerical results are calibrated with experimental results obtained from China Shape Science Research Center. To select a suitable tolerance model and a proper grid resolution, we also conducted a sensitivity study of numerical setup. To support this sensitivity study, we experimentally measured 3 global coefficients on the time operational conditions. These conditions are different in their advanced coefficients, and the 3 measured global coefficients are thruster coefficient, torque coefficient, and efficiency. This slide shows the global coefficients predicted with a different difference model and different grid resolutions. All results shows that the combination of nearly 3 million nodes and K omega ST model can obtain the best predicting effect, which is also stated as the final combination for our further investigation. To better identify the vortex structure in our case, we testified the ability of 4 vortex identification methods. And these methods cover 3 generations. It includes the vorticity method, Q criterion, omega method, and the Liutex method. This slide shows the vortex structures identified with these methods. We also selected 4 thrusters for different methods to find out a suitable thruster for further work. It can be observed that the shear effect significantly pollutes the identified vortex structure, and with a larger thruster, this shear effect is weakened. Furthermore, except for Liutex method, the other 3 methods offer to filter the shear level while retaining the main vortex structure. And the Liutex threshold of 200 can obtain the best identification method, identification effect. In the next, we discuss the correlation between vertical flow and hydraulic loss. Before this work, it's necessary to understand the vortex structure in our case. Therefore, we utilize the Liutex method to identify the vortex structure. In this picture, 4 typical flow structures in the other gap are especially marked. The flow structure 1 is the gap flow between the rim and the shell, and the flow structure 2 is the weak vortex. Furthermore, powerful vortex structure marked as 3 and 4 also exist inside the upstream and the downstream gaps. We further discuss the spatial evolution of these structures. This slide shows the contours of Liutex magnitude at different locations. It can be observed that the upstream gap vortex 4 and the downstream gap vortex 3 exist at all patients, where the weak vortex 2 only exists at the final position, which is near the trailing edge of the blade. Furthermore, when the weak vortex 2 is finally formed, some changes happen in the downstream gap vortex 3. It indicates the local flow separation can affect the gap flux. The gap flux is of great concern for our design of shaftless rim-driven thruster. To visualize this effect, we depicted the gap streamline along with the distribution of leakage flux. The direction of the gap streamline is upstream. It suggests the backflow phenomenon inside the gap. Furthermore, the maximum of the leakage flux always exists. The other region of weak vortex formation. It indicates that the flow separation is an important factor of flow instability, which can not only produce the weak vortex, but also increase the leakage flux. After understanding the vortex structure in our case, let's check the hydraulic loss raised by vertical flow. This section is based on the entropy generation theory. This theory can measure the local hydraulic loss raised by flow structure. In this theory, the hydraulic loss mainly consists of direct dissipation and turbulent dissipation. For K omega ST model, the entropy production rate due to turbulent dissipation can be further modeled as this equation. And for vortex structure, the local velocity gradient will be increased. And according to this equation, the increased velocity gradient will enhance the value of these variables. It indicates that the flow entropy production rate can be greatly enhanced due to vertical flow. This slide shows the distribution of entropy production rate at different locations. It can be observed that three regions, the hydraulic loss mainly occurs at three regions, which are the upstream gap, the downstream gap, and the flow separation region. As discussed before, the regions are with powerful rotational motion. It suggests the close relationship between the hydraulic loss and the vertical flow. Furthermore, the hydraulic loss raised by the mixing of the weak vortex 2 and the downstream gap vortex 3 is especially significant. It indicates this mixing should be paid greater attention because it can simultaneously aggravate the flux of backflow leakage and raise a significant hydraulic loss. Finally, we come to the conclusions as follows. Firstly, feasibility of different vortex amplification methods in the vertical flow inside the shaftless rim-driven thruster is compared thoroughly. Only Liutex method can filter the shear lever while retaining the main vortex structure. Secondly, with the assistance of Liutex method, the main flow structures are clearly identified, which are the gap flow, weak vortex, upstream gap vortex, and the downstream gap vortex. The upstream and the downstream gap vortex exist at all patients, where the weak vortex only exists near the trailing edge of the blade. And the last conclusion is that based on entropy generation theory, a closer correlation between hydraulic loss and the vortex structure is found. Greater attention should be paid to the mixing of weak vortex and the downstream gap vortex, because it can agree with the flux of backflow leakage and risk a significant hydraulic loss. About my presentation. Thanks for your attention.
Okay, thank you. Is there any question for the speaker? Is there any question?
Oh, well, no, but looks like not very active. Well, I think that is very nice work, and I know not. And I just have some questions. First, did you ever try? I think in your case, you talk gap vortex or vortex leaking is important. The vortex leaking is very important. Or you talk about gap vortex. Did you try a Q method to study the gap? Well, I know that. Then why you cannot use a Q method? What is it? I don't know. It's maybe not good. So did you adjust it, the Q threshold? If we adjust the Q threshold, what happened? Why you said only the Liutex method may be good for the gap, especially for the gap vortex or leaking vortex. So why are you saying that? And did you try Q method or other method? My question. Well, I know you try, but I just said this is one threshold. Did you try different threshold?
Yes, I have tried a different threshold of Q criteria. With the largest threshold, the share level, the share level just there is there, but there exists. So where there exists. Well, in our case, where only the Liutex method can keep the main vortex structure of concern. Concern when filtered the share level. So after this comparison, or come to the conclusion here, except for Liutex method, the other method cannot obtain such a ideal effect here.
Okay, my understanding is that no matter how to adjust the threshold for the Q method, the share also there. Share you cannot filter it, right? But of course you can get a too larger Q. Maybe it's no vortex structure, right? Yeah, too large. For example, you have no. But Liutex, you can adjust it also. Liutex as a threshold, but the share can be filtered, and the leaking, vortex or other, you talk top and rear vortex still there. But share disappeared, right? My understanding is right. So if we study the leaking vortex, the only the method is Liutex can still keep the vortex structure while the share disappear, right? My understanding, right?
Yes.
Yeah, from the Jiao Tong University, Shanghai Jiao Tong University, it sounds to me, well, they get a similar conclusion with you, but they also try the Liutex omega method. But here, I believe you only talk about omega method. Now, omega method sounds to me still have share. So you didn't talk about Liutex omega method. So my suggestion, you may try that Liutex omega method to see what happens. But right now, I think it sounds to me more clear. You cannot use vorticity because shares are there. Then Q also share contaminate. This is still a share, but you cannot give too large Q threshold, then you get nothing. That's empty. So what you want to do, you want to just fill the share, still want to keep the major vortex structure like leaking vortex and top and rear or vortex, they are still there. Then you have to use the Liutex method, to my understanding. Okay.
Yeah.
Okay, thank you. Yeah.
Thank you for your comment.
Okay, is there any other question? If there's no any other question, our session 10 will end here. Okay, next session will begin in 2 minutes. Thank you.
Hello, my name is Oscar Alvarez. I will be your host for session 11. We're going to take a 10-minute break before we start.
And we called the absolute diffusion stage. And the final stage is a skewing dissipation stage. And the second result, hairpin vortex is a typical vortex structure in the turbulent boundary layer. And numerical results show that they present in large quantities in turbulent flow. The hairpin vortex is composed of a span-wise vortex as head and a pair of quasi-string-wise vortices as legs, and it is inclined to the string-wise, span-wise plane. So we set up this light sheet setup. In our previous research, we captured a complete 2D hairpin vortex using the moving single frame and long exposure method. By setting different angles, we captured a symmetric hairpin vortex at 53 degrees. And as shown in this picture, the 2D hairpin vortex structure can be divided into 5 parts. A and B are vortex legs, and C and D are legs. The E is the head, and these pictures are the evolution process of the hairpin vortex. In the first 2 pictures, it is symmetric, and the left vortex legs is an ellipse. And under the impact of upwards and downwards, it gradually turns round. At the third picture, the whole vortex structure becomes longer and the left leg is a cycle. Also, it is no longer symmetric. And in the last 3 pictures, the hairpin vortex gradually dissipates. The legs remains for a longer time. And this is the parameter. And for more analysis, we set up the same light sheet inclination in the moving PIV experiments. And the left pictures are Liutex magnitude, and the right pictures are vorticity perpendicular to this plane. And for comparison purposes, here is the DNS result of a single hairpin. Here is the Liutex isosurface. And here is the diagram of the light sheet and the vortex. And as shown in the vorticity contour, there are 2 pairs of reverse rotating vortices. And here is the vortices distribution. C and D are vortex legs. A is the neck and B is the head. And since the head may be inclined, it's not a totally span-wise vortex, so it can be captured in this direction. And the position of the four parts gradually disperses, showing that the hairpin vortex is stretched. It is consistent with the numerical results. And from these pictures, we can see that the Liutex can well identify the vortex region. The regions surrounding the vortex are clean and not contaminated by such shear stress. And on the left, show the R integral over time for the four part of the hairpin vortex. And due to the characteristics of inclined photography, this method can not always get the cross-section of the hairpin vortex, and the image quantity is lower than the string-wise normal plane. So the R integral of the hairpin vortex is not as stable as the vortex generation results. And these figures shows the R and area variation curves for each of the four parts of the vortex. And for the vortex neck and vortex necks, the strength and size of the vortex both increase and then decreases. And vortex legs are closer to the wall, and the curves fluctuate more frequently. The vortex leg is affected by the viscous force, and the data fluctuates more. And as for the vortex head, the figure is different from other parts because it is far from the wall. And the development of the hairpin vortex head is divided into four main parts, such as the last results. And first is also the synchronous enhancement stage. And then it should be noted that there is a downward trend in the early part of the line graph, presumably because the last hairpin vortex head has not been completely dissipated. And in the second stage, the vortex intensity continues to increase while the vortex size remains almost constant. And this phase is the absolute growth phase. And similarly, this is the absolute dissipation phase stage. And the first stage, the vortex size and intensity decreases simultaneously. This is a synchronous dissipation stage. And this is the vortex merging result.
I'm sorry, but the time is up. It's now 50 past, or it's 53 past, and the presentation was supposed to be over at 50. If you could really quickly wrap up your presentation.
Okay. And this is a vertex merging result obtained by moving PIV method. And Li Yuan has already introduced vortex merging process by the moving single frame long exposure time. Here is the parameters, and here is the two vortices. The vortex A and vortex B merges into one vertex. And this figures shows the R integral and the over time of the multiple vortices in the vortex merging process. And also it can be divided into the following three stages. And the intensity of the new merging vortex is the two, the vortex A plus vortex B. And the results are as below. The moving PIV method is an effective flow field measurement. And for tracking the evolution of vortex structure in the turbulent boundary layer, and the Liutex vortex identification can provide statistical analysis of evolution of vortex intensity and size, and the evolution of neck and legs of the hairpin vortex can be described as a process of enhancement followed by dissipation. And the head can be described as a four-stage process of synchronous enhancements, absolute dissipation or diffusion, and synchronous dissipation. And the two adjacent vortices with the same normal height and co-rotating direction will merge to produce a new co-rotating vortex, which will maintain a stable intensity for a period of time and then dissipate. That's all. Thank you for listening.
Thank you very much. I'm sorry about the time constraint.
Yeah. Let me say, a few words because of the time problem. We passed the time limit. Well, it sounds to me very impressive. But you use the moving PRV, but most people use PRV. You're moving PRV and to study the vortex structure. I think this is way incredible. So that's what I say. This is pretty, make us, more convinced about the DNA results. It looks like, compare very well. I'm supposed you use the Lagrange method trace the each vortex not helping. So mainly not helping vortex. It should growth and development and damping, something like that, something like to me. But what I hope you guys use the moving PRV, I think you need study more mechanism, the vortex generation, sustenance, development, something like that. Yeah, because of time, I cannot ask more questions. And anyway, this is very impressive work.
Thanks for Professor Liu.
Yeah.
Okay, so this session is finished. We have, we have until 10 we have until the next hour, until the next session. So we have a break until then.
No, we only have the 3 minutes rest.
Yeah, so if you want to keep asking questions, that's okay. But the next session starts in the next hour. Thank you all for coming to session 11 of the conference. And thank you all the presenters.
Okay. So we will start your next session on time, I think. Yeah, we still have 3 minutes. So
yeah, I think.
Who is the host?
Yes,
Yishen Gao.
Yeah,
Gao. Gao is here.
Yeah, totally. I'm here.
Okay, you're here. Okay, so we just start on time, I think. Yeah. That means take a few minutes, rest, a break. So. Dr. God, did you give a talk today?
Yeah, the first one. Yeah.
First one. Okay, first one is Yonghua Yan, I think. Yeah, it's not.
Professor Liu, you missed the Dr. Gao's presentation.
Yeah, talk. Okay. So Dr. Gao was the first one today, right? Okay. But I would like to listen. Okay. So, well, we can talk later. Yeah.
Okay, now we begin the last session, and thank you everyone, and good evening, good morning, and good afternoon, everyone. And this is the last session of today, also the last session of our workshop. And this is Yishen Gao from Nanjing University of Aeronautics and Astronautics, and I'm pleased to be host the last session. Now let me welcome the first speaker, Guo Qiangtong from Northeast Agricultural University, China. And the topic is application of third generation of Vortex identification for straight braided vertical axis wind turbines. Now welcome Guo Tongqiang. Can you hear me?
Oh yeah, I'm here.
Oh, okay. You can start now and open screen share. Okay.
Hello everyone, my name is Liutex. I'm from Northeast Agricultural University. The topic of my report today is the application of third generation of Vortex identification for straight-bladed vertical axis wind turbine. I will report on the following four aspects: their background, research method, results, and summary. First is the background. Humans have been exploring ways to harness wind energy for centuries. As early as the 10th century, the Prussians developed the vertical axis wind turbines to green grind and treated their cells. There are primitive windmills. In the most recent decades.
Oh, sorry. Hey, can you turn up the volume? I think it's not clearly.
Maybe this is recorded, so the sound is not good.
Yeah, I think it's a video. Yeah. Oh.
We cannot hear you.
Yeah.
Oh, when you share your screen, there's so unshare your screen, and then when you share your screen again, there's an option to share the computer audio.
Yeah, I cannot hear anything.
Yeah, you need to stop sharing your screen, and then share your screen again, and then when the little thing, the window pops up, there's an option for you to share your computer audio.
Hello everyone, my name is Tongguo Qiang. I'm from Northeast
Okay, thank you.
University. The topic of my report today is the application of third generation of Vortex identification for straight-bladed vertical axis wind turbines. I will report on the following four aspects: their background, research method, results, and summary. First is the background. Humans have been exploring ways to harness wind energy for centuries. As early as the 10th century, the Prussians developed the vertical axis wind turbines to grind grain and irrigate their fields. There are primitive windmills. In the most recent decades, the energy industry has witnessed a phenomenal worldwide increase of wind energy harnessed by wind turbines. A wind turbine, also known as a windmill, is an energy conversion device that converts wind energy into mechanical, electrical, and thermal energy. There are many ways to classify wind turbines. There are two main types, according to the relative position of rotor shaft to the ground. They can be divided into horizontal axis wind turbine and vertical axis wind turbines. According to the working principle, they can be divided into lift-type wind turbines and jet-type wind turbines. Wind turbines began to develop significantly in the 20th century, aided by aerodynamic research in the aircraft industry. The figure on the right shows large-scale horizontal axis wind turbine and the small-scale horizontal axis wind turbine. Currently, large-scale wind turbines are basically horizontal axis wind turbines. The figure on the right shows a straight-bladed vertical axis wind turbine, tractive vertical axis wind turbine, and diverse vertical axis wind turbine. The straight-bladed vertical axis wind turbine is the classic type of Vortex vertical axis wind turbine. It has a high share in the small-scale wind turbine market, with their advantage of aesthetically more appealing, wind direction independence, simple structure, low noise, mechanical components close to the ground, low installation and operating costs, as well as their suitability for off-grid power generation operation. It mainly consists of blades, rotating shaft, generator, and control device. This is the main objective of our study. There are significant differences between horizontal axis wind turbines and vertical axis wind turbines. In terms of wind control, blade control, transmission and operating mechanism, tower shadow effect, wind energy utilization ratio, and starting performance. In terms of wind direction control, small-scale horizontal axis wind turbines require rudders, and large-scale horizontal axis wind turbines require yaw mechanism. For vertical axis wind turbines, it can accept wind from all wind directions without the wind pairing device. For blade control, horizontal axis wind turbine need to control the speed by controlling the mounting angle. For vertical axis wind turbines, generally they don't use the method of controlling the blade mounting angle for speed regulation. In terms of transmission and operating mechanism, it needs to be installed on top of horizontal axis wind turbine. For vertical axis wind turbine, it can be located on the ground. In terms of tower shadow effect, horizontal axis wind turbine installed downstream and are subject to a large tower shadow effect. For vertical axis wind turbines, the effect is smaller. In terms of wind energy utilization ratio, horizontal axis wind turbine higher. The lift table vertical axis wind turbine is comparable to the horizontal axis wind turbine. In terms of the starting performance, for horizontal axis wind turbines, at a low wind speed, starting performance is general, and large-scale grid connected wind turbines require some starting, depending on the generator. For vertical axis wind turbines, a starting device is required for left-tip vertical axis wind turbines, while it is not required for right-tip wind turbines, which have ideal starting performance. Straight-bladed vertical axis wind turbines have a high power coefficient, but the starting performance is poor. The wind guiding device is an auxiliary device designed to enhance the starting performance of straight-bladed vertical axis wind turbines. The objective and significance of this paper are to select a more suitable method for flow-field vortex research of straight-bladed vertical axis wind turbines by comparing the identification result of omega method and Q method. This research will provide a reference for the selection of flow-field vortex identification method for straight-bladed vertical axis wind turbines. The identification and optimization of vortex in the flow field is an effective method to enhance the performance of straight-bladed vertical axis wind turbines. In the past studies, the Q method was the main method for vortex identification, but the poor robustness created difficulty for this study. The third generation of vortex identification method, which have a higher robustness, bringing convenience to the study of straight-bladed vertical axis wind turbines. In this research, straight-bladed vertical axis wind turbines with and without wind guiding device are studied, and their flow-field vortex are identified using omega and Q method respectively. And the different thresholds are selected in the respective range of the two methods, and the results obtained by the two methods are compared, mainly to compare the threshold sensitivity and to select a more suitable method for straight-bladed vertical axis wind turbines. The next step is the research method. The following are the theoretical research methods, including model method and numerical simulation. The most popular methods for studying straight-bladed vertical axis wind turbines are wind tunnel test, numerical simulation, and PIV. Among which numerical simulation are considered to be the most promising research choice, so we use the numerical simulation method to study. The four-bladed straight-bladed vertical axis wind turbine of NACA 0018 FL tape was used in the study. The blade chord length is 125 mm. Rotor diameter is 600 mm. Rotor diameter is 500 mm. And the wind speed is 8 meters per section. The omega and Q method are used to identify vortex in a dynamic flow field with a tip speed ratio of 1. The numerical simulation was performed using ancestry, and the computational domain is shown in the figure on the left. The total number of grids is 20 million, and the transition simulation are performed. The grid is cost because of the limitation of the computer. The next step is results. This is the velocity distribution of different sections of straight-bladed vertical axis wind turbine with and without wind guiding device. The low speed inside the straight-bladed vertical axis wind turbine can be clearly seen from the velocity distribution. And those low velocity zones are the results of the vortex. This is the result obtained by using the Q method. Because the valid range of threshold value for the Q method is greater than 1 than 0. The threshold value selected in this study are 100, 1,000, and 10,000 respectively. From the figure, it can be seen that in the Q method, the variation of the taken value has a large impact on the results. The often threshold is between 100 and 1,000, but the range is still too large. This would be detrimental to the optimization of straight-bladed vertical axis wind turbines. This is the result obtained by using the omega method, because the threshold range of omega method is from 0 to 1, and the recommended range is 0.52 to 0.6. The threshold range chosen in this paper are 0.52, 0.56, and 0.6. From the figure, it can be seen that in the omega method, the robustness is higher, and the value taken to dot have a significant effect on the results. It can get stable results very fast. This will facilitate to optimization of straight-bladed vertical axis wind turbines. This is the straight-bladed vertical axis wind turbine and horizontal axis wind turbine profiled vortex during rotation. The vortex generated by the upstream blade is broken by the impact of the downstream blade, resulting in a more complex vortex in the flow field. The flow field vortex of straight-bladed vertical axis wind turbine is more complex than horizontal axis wind turbine. A convenient and accurate vortex identification method plays a very important role in optimizing the performance of straight-bladed vertical axis wind turbine. The Omega method is a good choice. The Omega method was used for vortex identification of the flow field of a straight-bladed vertical axis wind turbine with and without wind-guided device. The vortex of the flow field is different at each cross-section of the blade, especially the top of the blade and the middle of the blade. The two-dimensional simulation cannot accurately represent the flow field characteristics. This is the identification of the straight-bladed vertical axis wind turbine with and without wind-guiding device in the flow field vortex during precipitation. Using the Omega method, the vortex of different size in the flow field are well represented. Finally is the summary. In this study, straight-bladed vertical axis wind turbines are used to identify the vortex in the flow field by using the Omega method and the Q method respectively. The result show that the Omega method can produce stable results quickly. The Omega method has good performance in identifying the vortex at a different scale in the flow field. The Omega method is an efficient and fast method in the study of vortex in the flow field of straight-bladed vertical axis wind turbine. Okay, thank you.
Okay, thank you so much, Guo Xiangtong. Any question?
Well, if not, I just give some comments. I think the topic is important because that's related to clean energy. So that's very important. There's a wind turbine. And I think some people may argue say that we don't care about the vortex. We don't care about noise because they're far away. They're in the countryside. So they could say that. But well, we do the scientific research. We still want to study the vortex structure. So that's the first one. Second is I suggested, because it sounds to me you use the Q method, you use the Omega method. Really, they are similar, but Omega method is really not very sensitive to the threshold, but Q is sensitive. Yeah, that's what I see from your talk. My suggestion is, if possible, you could try the Liutex method and the Liutex Omega method. Maybe better can show the more clearly vortex structure. I think both Q and Omega method still share contaminate. That means some structures are shares. And so it is better to use Liutex or use Liutex Omega method. Of course, I think the best one, it should be Liutex Colline, because you don't need any threshold. You can see the vortex strength, where it's weak, where it's strong. Well, this is for scientific research that's may not be related to the social or economic, because we don't care. We don't care about noise, so we don't care about the vortex. So the people, some people could say that, but we just study science. So thank you for the very nice talk.
Thank you very much.
Okay, I think okay. Thank you, the first speaker. Now we welcome the second speaker, Yufang Yang from Beihang University. The topic is novel control strategies on leakage flow for turbine rotor with squid tip. Yufang Yang.
Okay, can you hear me?
Oh, yeah.
Oh.
Okay.
Okay.
And can you share your screen?
Yeah. Can you see my screen?
Oh, I can see anything. Okay, okay, it works. Okay.
Okay. Hello, everyone. My name is Yufan Wang from Beihang University. I'm sorry for that. There is some problem from my slide. Can you hear me?
Yeah. I can see PPT.
But I can't.
We cannot hear if you are talking.
Look, can you hear me?
We can hear you, but we cannot see your presentation. Your you didn't go to slide, yeah, animation. Yeah, you should go to slide animation.
There is some problem. What? I'll share my screen again. I'm sorry, there is something wrong in my computer. Can you hear me now?
Yes.
No, we can not see you before. Yeah. We can see you before, but you just didn't show us the slide show. So just yeah.
We can
cannot
hear
see
you,
now.
but we cannot see anything.
Yeah, we cannot see you. You know, at the beginning, we can see your PPT file, but we cannot show the slide show. So it just restart from beginning, I think. Yeah, then try to share screen and then try to show your PPT, your presentation. So you just redo it. Yeah.
Everyone, can you hear me now? There is some problem with my computer.
Yes, we can hear you.
I'm sorry for that. And I can share my screen.
You cannot share your screen?
Yes, there is something wrong in my computer.
Well, then in that case, I think it is better to move the next speaker, and then you can have time to fix your computer.
Okay. Thank you very much.
Yeah. Okay. Dr.
Okay.
Gao,
Okay.
Next, the next speaker to talk.
Next speaker, okay.
If he's here.
Okay, I check. 知议员，next 知议员 Are you here?
Yes, yes,
Oh,
I'm
okay,
here.
okay, thanks. Can you start now?
Yes, okay.
Okay,
Share
okay.
my screen.
Oh, okay. Now let's welcome next speaker, Zhi Yiyuan from China University of Chile. And his topic is study on fluid ball noise around a cylinder based on vortex sound theory with Liutex decomposition. Now welcome Zhi Yiyuan.
Okay, thank you. Thank you. Everyone can see the slides and help.
Yeah, yes.
Okay. Good morning, everyone. My name is Zhi Yuan. I come from China University of Petroleum, Beijing, and this is my topic. I'll give the presentation in the following four parts. The first is background. The flow-induced noise over cylinder is widely studied as its typical geometry, and the prior fluctuation caused by water shedding could is noise generation and brings the noise pollution, which influence the health of creatures and affects the concealment performance of vehicles. Thus, it's meaningful to investigate the noise generation mechanism from the perspective of the vortex and develop what control methods to reduce noise. There are two popular methods to predict noise. The most general form is the FWH method, and it can be seen that the form has less relationship with vortex. Well, Paul Bell proposed vortex sound equation, which shows the sound duration is associated with the dynamics of vortices. And considering the Liutex decomposition by Professor Liu's group, it provides a new perspective to calculate the sound pressure originating from rigid rotational motion and shear. It's an attempt to discuss the effects of rigid volatility and shear on acoustic participation. The next is numerical setup. It's a simple structure, and the what sound equation is solved by the user-defined scala in the fluent. The three UDS-defined macros were used to solve the unsteady term and the diffusivity term and short term in the work sound equation. And there are also some variables to evaluate the noise field, the sound field, and the flow field. The sound the root mean square sound pressure is calculated by fast Fourier transformation with 124 sample points. And the entropy production rate is to evaluate the loss. And there are also some monitoring points to measure the sound directivity and the sound characteristics at the different wake regions. To validate the simulation, the experiment that auto is selected. The change of the sound pressure level calculated by what sound methods agrees well with the choice results. We can see the vortex streets. It can be seen that the Liutex shows a more clear vertical region without the steering combination. And this is the isosurface of omega and colored by entropy production rate. We can see that the high loss region near the cylinder and the low loss region. And this figure shows new counter of shear magnitude at the slice. The vortex region with strong shear is located at the areas with high loss. When the shearing force becomes weak, the vortex becomes more stable as the loss is very low. And then these figures show the relationship between vorticity and irreversible loss. The shearing part takes a large proportion of the vorticity, and in the shading areas, the energy decreases sharply downstream. When the vortices are far away from the cylinder, the energy loss remains unchanged and at a considerably low level. The right figure shows the distribution along with a line of V, and there's no apparent change except near ring wall, where there is a large volatility and shear magnitude. And the relationship between vortex shading and noise is shown in the figures. The left figures illustrates the sound pressure fluctuation and the static pressure at the point M. The point M is nearing the wall. The change of the sound pressure has two distinct peaks at 128 Hz and 64 Hz, while there is only one peak at 64 Hz in the pressure fluctuation. It's obvious that the 128 Hz is from the vortex shading from the upper and the bottom sides, while the 64 Hz results from the shading from the bottom side. Considering the shearing effect and the radial rotation effect on the sound pressure, it's shown that the shearing parts of volatility mainly contribute to the noise compared to the rotational parts. And the similar conclusion can also be seen in the point D. However, as the point D is located at the downstream of the vortex shading, the pressure fluctuation is affected by vortex shading from the two sides, so there is two distinct peaks, and the amplitude at the low frequency is smaller than it's at the shading frequency. In order to investigate the changing law of sound pressure along the downstream, the change of vorticity, sound pressure, and pressure is shown in this slide. The left figure shows the fluctuation at the point B, and the vorticity, Liutex, and the shear magnitude has only one distinct peak at the shading frequency, while the sound pressure at 64 Hz is higher than it at the shading frequency. The same phenomena also occur at point E. As flow downstream, all the values of these variables decrease, and the radial rotational effect on the sound pressure becomes more negligible. And looking at those monitoring points, the total sound pressure level and the time average Liutex and shear is shown in these figures. It shows that the total sound pressure level has a close relationship with Liutex and shear, and as the Liutex and shear decrease, the sound pressure becomes lower. And the last is the sound directivity. The plot indicates the dipole part of the convex field around the center. The shading of vertices from the cylinder surface induces alternate pressure fluctuation on the top and bottom surface of the cylinder. And then this pressure fluctuation acts as a dipole type accounting source in the surrounding medium. It can also be seen that the steering part plays the major role in the noise generation compared to the rigid rotational part. And finally, there's the conclusions. The main conclusion of the noise is the steering part of vorticity mainly contribute to noise compared to the rotational part. And the dominant frequency of sound pressure is closely related to what sounds vortex shading from one side. And the sound pressure originating from the rotational part only affects the tunnel noise at shading frequency and its half frequency, while the sharing effect generates broadband noise. Okay, that's all. Thanks for your attention.
Okay, thank you, Zhi Yuan. Very interesting results. Any question?
Well, I think because of the time limit, I just give a couple questions. Yeah, yeah, this is a very important topic. Yeah, that's what we are interested. Where the noise come from? From your presentation, I think first you show we need a decompose. This is in the middle. It is vorticity. You need a decompose two parts, Liutex and the shape. First, yeah. Then second, you say for the energy, lost is mainly caused by shear. You going down. That's your conclusion. Yes, right?
Yes.
Yeah, the energy loss method caused by shear, not by the Liutex. Liutex doesn't cause the energy loss really because the rigid rotation. Yeah, that's your conclusion. That the third conclusion mostly concerned where is noise come from. So you show us going down. Yeah, you show us where the frequencies looks like the noise. It looks like similar to the Liutex. Is true or not true? Your frequency. Not exactly
the difference. You can say the
128. Yeah, you say the noise frequencies is different from Liutex or same?
Yeah, it is different. We can say the dominance of the sound pressure, the noise, is 64 Hertz, while the Liutex, the shear and the vorticity is at the vortex shading frequency, the 128 Hertz.
128 is your noise, right? It's a vorticity?
Yes, it's a vorticity and Liutex magnitude and the shear magnitude. The SP is the sound pressure.
The spectrum. SP is a spectrum, right? Or pressure spectrum, right? Yeah. And so what's your conclusion? So the noise frequencies is really determined by vorticity or shear by shear.
Yeah, by shear. We can see the shear is the blue. The color is blue, and the vorticity is black. The shear is close to the vorticity, and
shear is close to the vorticity. And the frequency is correlated with shear. Is correct? Noise is noise. That's your pressure. Fluctuation. So it's a spectrum of the sound. It is correlated with shear. That's your conclusion, right? With shear.
Yes,
That's correct.
Yes.
Of course, the share is more broad, something like that, not only, but the dominant frequencies is the share frequency. Is correct?
I explain that the sound source, you can see the sound source is not only
with sound source, not the
not
sound,
only
the sound
the Liutex share. It's yeah, you can see that the right hand is the sound source.
Yeah. That's the sound source. Okay.
Yes.
So then your sound frequencies is determined by what? By the share or by the Liutex?
By share.
By share, not by Liutex.
Yes, not Liutex.
You say they yeah.
Yes, Liutex magnitude, I guess it's because the Liutex magnitude is too small.
Well, I only talk about the spectrum. No matter they're big or small, I just
In this, yes, this is spectrum.
That's the main source.
Rate line, the rate line is the Liutex, and we can say rate line. The amplitude of rate line is about.
That's you sure. It sounds to me the main source is Liutex. Really, this is figure is correct. Yeah, I know the frequency may be, this like a subharmonic.
I'm sorry, it's time for next presentation. We can talk after next meeting.
Okay, we talk later. Yeah, we talk later.
Okay, we can contact via email.
Okay.
Yeah, I guess. Okay, thank you. Yeah.
Okay, thank you, Zhi Yuan.
Yeah, thanks. I'll stop myself.
Yufan Wang, are you here?
Yeah, I'm here.
Okay,
can you hear me?
Now, can you share your screen?
I'll try again. Now, can you see my screen?
Yeah, I can see.
Okay. Maybe I should present my presentation just like this. Hello everyone. My name is Yufan Wang from Beihang University. It's my pleasure to attend this conference and give a presentation on our research work. The topic of my presentation is load control strategy on tip leakage flow for turbine rotor with screening. As shown in the slide, my presentation includes 6 parts: the introduction, research methods, and then strategy for inhibiting tip leakage flow and suppressing the breakdown of tip leakage vortex, and then the control effect of company strategy. And finally, the conclusion. At the beginning, I'd like to briefly introduce the research background. In air engine turbine, there are many vortex structures with different size and intensities, which has a great influence on the aerodynamic performance of turbine. From the development of turbine aerodynamic design methods, fan flow organizing is an essential step in the pursuit of high performance turbine. In particular, the control of various vortices is important. In the turbine rotor passage, the tip leakage flow is inevitable because of the geometrical characteristics of rotating machinery. The tip leakage flow and the vortex are the main source of aerodynamic loss in operation turbine. And therefore, the control of tip leakage flow and the tip leakage vortex is of great significance to improve the aerodynamic performance of turbine. At present, the commonly used control methods include screen tip, lineage tip, TV injection, plasma actuator, and so on. Among the above-mentioned methods, the screen tip is the most effective and widely used. Previous studies show that the mechanism of screen tip blocking tip leakage flow is a pneumatic library sealing effect. As we all know, the library structure has a great influence on the leakage performance. Then the question is how to further optimize the geometry of the screen tip to enhance the pneumatic library sealing effect and block the leakage flow. In addition, there is still another difficulty in the control of tip leakage vortex, such as the vortex breakdown. Vortex breakdown could lead to extra mixing loss and cause the decline of turbine aerodynamic performance. Therefore, vortex breakdown needs to be controlled. To solve the above-mentioned two problems, we performed the numerical simulations on a transonic high-pressure device with a screen tip. The research object has a low aspect ratio and a high Reynolds number, which is the typical geometric and aerodynamic characteristic of high-pressure turbine. The Reynolds averaged Navier-Stokes equations are solved in the simulation, and the turbulence model is a shear stress transportation model. The grid is generated with SM and out-grid file in order to ensure that the numerical results are not affected by the grid density. We verify the grid independence. According to the tip leakage rate and turbine stage efficiency, grid flow can ensure the numerical accuracy. Next, let's consider the first of the two questions raised earlier. How to further optimize the screen tip to control the leakage flow? According to the research of Prakash, we know that the inclined pressure side ring can enhance the blocking effect on the leakage flow, which is the result of the enhancement of separation bubble at the top of ring. Similarly, we can also use the inclined second side ring to enlarge the separation bubble at the top of second side ring and further reduce the leakage rate. With the Liutex method, it can be found that there are complex vortex structures inside the cavity, and the scraping vortex plays a dominant role. And here it can be seen that the new structure could increase the flow angle of tip leakage flow, which has a significant impact on the development of separation bubble. The orthogonal decomposition of velocity is performed according to the figure. Magnify the region of the separation bubble. The black separation streamline indicates the indicates that significant increase of separation bubble. This is inseparable from the increase of the leakage flow angle. In addition, the tangential velocity is extracted in line 1 and line 2. Obviously, the tangential velocity of leakage flow is reduced in the new structure. According to the distribution of leakage rate as the clearance outlet, the leakage rate of the new structure is reduced by 4%. Overall, by analogy, the inclined internal surface of section side ring could enlarge the.
Can y'all hear him?
Yes. Can you hear me? Hi everyone, can you hear me?
Yes, I can hear you. What about others?
Okay.
Our host, Yisheng Gao, can you hear?
Yeah, I can hear.
So you can continue your presentation.
Yeah, continue.
Okay.
Sorry, it was just me. Sorry.
Okay. And enlarge the circulation bubble and significantly reduce the leakage rate. Restraining the leakage flow can indirectly control the formation and the development of tip leakage vortex, but can suppress the breakdown of it. In the prototype, there is a reverse flow region in the vortex core, which indicates the breakdown of tip leakage vortex. Here we refer to further explanation for the breakdown of quasi-symmetrical vortex, as shown in the formula. The breakdown of quasi-symmetrical vortex is obviously affected by the far-field pressure gradient and the circulation of the vortex. Similarly, the breakdown of tip leakage vortex can be affected by the adverse pressure gradient and the circulation of the tip leakage vortex. According to the distribution of Mach number, there is a lower shock wave upstream of the breakdown position of the tip leakage vortex. It is the existence of this lower shock wave that leads to a strong adverse pressure gradient at the 18 axial chord length, and then leads to the backflow of the fluid in the tip leakage vortex core and the breakdown. Therefore, the strong adverse pressure gradient is one of the reasons for the breakdown of tip leakage vortex. In addition, the circulation may affect the vortex breakdown. Omega method is used to identify the boundary of tip leakage vortex and determine the area and the circulation of vortex as different cross section. The vortex breakdown could lead to the sharp increase of vortex core radius. According to this, we can determine the position of vortex breakdown. Downstream of the tip leakage vortex breakdown, the variation of circulation is small, which is obviously not the main factor leading to the breakdown. The significant change of real number indicates the sharp degrees of streamwise velocity, which further confirms the influence of strong adverse pressure gradient. Based on the above analysis, we constructed a new blade tip to reduce the intensity of the adverse pressure gradient as shown in the figure. According to the pressure distribution, it can be found that the adverse pressure gradient of the new structure appears more downstream. In addition, the slope goes down, which indicates the intensity of adverse pressure gradient of the new structure decreases significantly. With Liutex method, we found that the intensity of the tip leakage vortex is significantly improved in the new structure, which implies that the breakdown of tip leakage vortex has been effectively controlled. Comparing the loss distribution near the tip leakage vortex, which can be found that the breakdown in the prototype leads to a large amount of loss surround the vortex core, while the corresponding loss is significantly reduced with the disappearance of vortex breakdown in the new structure. Overall, The inclined external surface of such side ring could effectively reduce the intensity of adverse pressure gradient and delay the accuracy of each. This is conducive to suppressing the leakage vortex breakdown and reducing the mixing loss caused by it. The two modeling strategies above mentioned are from the perspective of leakage flow control and vortex breakdown control, respectively. Considering the company effect of them, we constructed the blade tip shown in the figure. From the perspective of leakage rate control, the effect after company is not as good as S1, which is purely used to control leakage rate, but better than S2. In terms of overall aerodynamic performance, that is turbine stage efficiency is improved with the company strategy, and the aerodynamic benefit is more significant. The total pressure loss distribution further reflects that the company strategy has a better control effect on the aerodynamic loss. Finally, we get some conclusion. Firstly, the inclined internal surface of suction side ring could increase the angle of tip leakage flows out of the cavity, enlarge the separation bubble, and reduce the leakage rate. And then the breakdown of tip leakage vortex is mainly affected by the strong adverse pressure gradient, and the circulation has a few influence on it. The inclined external surface of such side ring could reduce the intensity of adverse pressure gradient and delay the accuracy of it, suppressing the vortex breakdown. The above-mentioned two strategies for the control of leakage rate and vortex breakdown can be combined to obtain a better aerodynamic benefit. And that's all of my presentation. Thanks for your attention.
And thank you so much, Yufan Wang. Any question? I think we don't have 30 minutes left.
Well, we don't have much time, and let me ask a couple
Only
questions.
three
Yeah. Well, a couple questions. Yeah, first, my impression is you try to improve the engine design by reduce the loss of the leak. Yeah, vortex. Something like you got two ways. One is reduce the leaking. The second is try to avoid the leaking vortex breakdown, something like that. Yeah, so you try to control this. Well, one question is, did you try the other vortex identification methods? And how about this method for the leaking vortices?
Yes. In here, I use the Liutex method and Omega method. And
Q, we try Q, not Q. Q method, no. No, I know you use the Liutex method. I know that. Did you try the Q method or you Q? Oh, that's Omega.
Q method. Yes. But I didn't present it in here, and Q have some problem like threshold and the shell contaminant.
Contamination. Okay.
Yes, contamination. And
so you only can use the Liutex method to avoid the shear contamination, something like that.
Yes, and Omega method, because Omega method is robust, and I can identify the typical vortex with the same threshold in different cases.
Oh yeah. Well, I'm also curious. You use omega method, pure ammonia, or Liutex omega method?
Yes, Liutex omega method. I try to use it, and I will use it in my future work.
Oh, okay. So currently it's just the pure omega method, right? Yeah, just omega method.
Yeah.
Okay. So your conclusion is if you can control the water breakdown, right? Yeah, you can control breakdown. You can improve the efficiency, right? Yeah.
Yes.
Control the leakage rate and water breakdown. So you talk about water breakdown is talk about the leakage, leaking water breakdown or regular water breakdown.
Here I'm talking about the leakage, tip leakage water breakdown, and that I refer to the.
So your method is try to get a strong adverse pressure gradient, right?
Yeah, and I refer to how the explanation for a breakdown of quasi-symmetrical vortex, and this is a quasi one dimension serial.
So if you don't have strong water breakdown, so your loss will be reduced, right? Your energy loss will be reduced. My understanding is correct. Yeah, the breakdown typically could be affected by adverse, that's adverse pressure gradient by circulation. Yeah. Okay, it's a nice talk. I appreciate it.
Thank you very much.
Okay. Thank you.
Okay, thank you.
Okay. Thank you, Yvonne. Thanks all speakers and host. And the session is the last session is over now. And before even conclusion, let's welcome our chair Iqian to say closing remark.
Okay, dear all, this is Yiqian Wang, your workshop chair. I thank you all for your valuable support. We have had a very successful workshop, many interesting and meaningful presentations. I believe all of us will benefit from these communications. I also would like to express my special thanks to Professor Liu for his great support, and Ms. Stephen for the organizing work. And hopefully we can have a live face-to-face conference in the future. And next, I would like to invite Dr. Liu first, and Stephen, and then Stephen to make some remarks. Dr. Liu, are you there?
Yes, yeah. I can hear you. Well, first I need to thank Dr. Yiqian Wang for his hard working to organize this very successful workshop. I think not only we have many speakers, we also have very broad, very deep research work, which is very impressive. Yeah, I really appreciate it. So then I also appreciate Stephen's effort. Yeah, with his effort, so our workshop can be successfully held. So I would appreciate it for the conference organizer, especially Stephen. And I think for the future, this conference, this workshop, just the beginning or just in the middle way. for us to deeply study turbulence and flow control and vortex science. Yeah, I hope we are do better. But after the conference, I believe Dr. Wang already signed a contract with the Springer. I think, yeah. Then we will publish a book, a report out the workshop. I think that's important, that we want to share our research with the world. That the publication of a book, it is important. I hope everybody, spend some time to modify, to refinement your talk. That's the one thing I hope you guys to do. We want to publish a wonderful book. The second, as not of very interesting talks, but I think I cannot understand all of them. So that's the first. I want to, if we can set a website, we can share this presentation or video with all the participants or with the public, so we can read this video again. But in addition, we may be communicated to each other for further discussion or the collaborations. So this is also important to get collections. The book is collections of our your paper and your maybe PPT, but the website could be the collection of all the presentations. For me personally, I want to listen again because some of them I don't fully understand, and also this is good for our more deep, more further discussions because we from different areas. Yeah, the last one. So we hope we can develop some collaborations with these participants because we're from different areas. Some from mathematical area, just for medically, mainly for the theoretical work. Some from experiment work. It's a lot different. And so some, I think most from engineering applications. So the only thing we can, further develop the good science for vortex, for turbulence, is the collaboration from, especially for different areas. That's more important. So that's the 3 points I emphasize. I hope we still keep communications, keep it possible. Could develop some collaborations. Finally, we want to. We can. At least with the turbulence is very complex, and with vortex is very complex. So we cannot say we just solve them. We at least we make a big progress, a big advances in the near future by our collaborations from different disciplines. Yeah, again, thank you everybody for your attending this workshop, for giving wonderful presentations. I just say, thank you, and thank you the chairman, and thank you the conference host. Anyway, I just really, from my heart, appreciate your guys' the efforts, your wonderful work, and and your participation. Thank you.
Well, that was a really insightful workshop, and I thank all the speakers who have given a part in this. Once again, I extend my gratitude to our plenary speaker, Dr. Lui, and our chair and co-chair, that is Dr. Wang and Gao, for making this workshop a huge success. And also hope to associate with you, which are next event in next year, that is in 22 in Valencia in November. So hope this time we have this in person, hopefully, and also love to have you all there. Thank you so much.
Dr. Wang. Dr. Wang, yeah. Dr. Wang, Dr. Wang not respond, yeah. Dr. Wang, yeah. Well,
I'm sorry. I didn't.
Okay, yeah.
Click the unmute, unmute button. Okay. So thank you all. Anyone want to make a further comment? Maybe Dr. Yisheng Gao, you want to say something?
Thank you all.
Okay.
Yeah,
so,
and yeah, also I want to thank you for the all the host, session host or session chairman for their hard working, and also I would thank you the coordinates. Yeah, that means we have coordinates in our U.S. delegate and Australia delegate. Yeah, actually it is coordinated by the Charles Notice and FAU. Yeah, they also spend a lot of time to work, but of course, the mainly it is organized by Dr. Yichen Wang. Really appreciate his.
I should say that Professor Liu and his team has greatly support the workshop. Without them, the conference or the workshop will not be so smooth. Thank you all, Oscar, FAU, and
any other
everyone
participants have something to say? Yes, welcome to say something.
Welcome to say something.
Okay.
I'll say some. Thank you for allowing me to be a part of this conference and allow me to also be the coordinator for the US and Australia delegates. And it was my pleasure to help out and make sure that this meeting was a success, and I believe it was. And like Dr. Leo said and Dr. Wong said, that I hope that this has inspired us to become, to collaborate and also find have found something new about using the Liutex methods and everything that will also inspire more research and more deep understanding of it. And thank you all for coming, and yes, that's it.
Thank you, Oscar.
Aris?
I want to thank everyone for that was a part of this conference. It's really nice to share Dr. Liu's work with everyone and see all the work that has been made because of his discovery. I think it's really cool. I think it's really neat. And I'm glad that I was given the privilege to see and all y'all's work and be a part of this conference. Thank you.
Thank you. You have something?
I would like to say something. So it was a great pleasure for me to attend this meeting, and thank you very much to Dr. Yisheng Wang and Dr. Xiaoqun Liu for making us the participations of this presentation, and it was a lot of practical research which we saw in here, and the use of the third generation Vortex. And yeah, thank you very much. It was a great experience.
Thank you.
Anyone else? Ife is cannot be.
Yes, Professor. Yes. Yeah, I would like to thank everybody for participation. I know it's really difficult to organize international students, especially all the the participants come from all over the world, and we need to negotiate with the time zone issue. Yeah, thank you for your hard work. Thank Dr. Wang for your hard work.
Thank you, Ife.
Looks Dr. Xia is here, Yu Xianxia. Yeah, Dr. Yuan is here. Yeah, Dr. Yuan, I'm really interested in your work. I think we are working in the same directions. So I hope I have the chance to continue to talk with you. And so while, yeah, I think we still have 3 people here. Yeah, like Yufang Wang, Yuan Ziyi, and Xia Yuxian. So do you have anything to say? Yeah.
Okay, Dr. Liu, if no one wants to say anything, we will close our workshop. Okay, thank you all. Thank you all. Thank you, Stephen.
Hope we see you soon for another conference, something like that.
Yeah. Okay. Yeah. Hopefully we can have a face-to-face live conference in the future, in the near future.
It's not decided by us. It's decided by the virus. So yeah, we hope. Yes. Yeah.
Okay. Thank you all, and the workshop has been closed, and we have had a successful workshop. Thank you all. Goodbye, and I wish you all the best.
Bye.
Yeah, bye-bye.
Yeah,
Yeah.
bye.
Bye. Thank you.
Thank you.
Bye.
Bye.
Yeah.
Bye. Thank you.
Yeah. Thank you so much. Bye-bye.
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 So now we are ending the session. Thank you so much.
Yeah, we're ending the workshop.
Yeah.
Actually,
Yeah.
yeah, I appreciate your
Maybe also the
technical support.
conference.
Yeah, yeah. In general, this is smooth. It really is. It is smooth, but we meet some problems. Some problem caused by me. Yeah, I forgot to turn off the microphone. So when I'm at home, so. I just talk to somebody, then sorry about that. But this is some problem with the internet. But in general, for such online conference, it is in general is successful. I think we didn't meet a big problem anyway. So yeah, thank you, Dr. Wang. Thank you, Stephen. Thank you for the technical support. So we will hopefully we will meet another time when we meet soon. Yeah. So. It's way late in the China already, so it's the good time in the US. Okay, we just say bye, bye, bye,
bye,
bye,
yeah, bye, bye. Oh, well, that was very insightful workshop, and I thank all the speakers who have taken a part in this. Once again, I extend my gratitude to our plenary speaker, that is Kevin Liu, and our chair and co-chair, Yikuen Yang and Yixing Gao, for making this workshop a huge success, and also hope to associate with you people in our next event on aerospace. So once again, I thank you so much, and we are ending the session as well as the workshop webinar. Once again, I extend my gratitude to all our speakers and moderators and hosts. Thank you so much, and bye-bye.